So, uh, Rakshi sir, it will be best if we start. We got almost 100 plus participant now. We will start. So, it will be best if you share the slides.
Very good morning, everyone. In the day 6 of faculty development program on smart health innovation, integrating imaging, sensor and biomaterials. Today we have 4 eminent speakers who will deliver their talk, and we are highly honored and privileged to have Professor Kunal Pal sir, who has joined this meeting, and we are very thankful that he has accepted our invitation to deliver the keynote talk. Dr. Kunal Pal sir has obtained his bachelor degree in pharmacy from the College of Pharmacy, New Delhi, India. He pursued further studies, completing his master in engineering degree in biomedical engineering at Jadavpur University, Kolkata, and earning a PhD in material science from IIT Kharagpur. Following this, Dr. Pal served as a postdoctoral fellow at Ryerson University in Canada, broadening his global perspective. In 2009, Dr. Pal began his professional journey as an assistant professor in the Department of Biotechnology and Medical Engineering at National Institute of Technology, Rourkela. His research primarily focused on biomaterial, drug delivery mechanism, food science, and innovative food design. Dr. Pal also possesses expertise in biomedical instrumentation and signal processing, showcasing his multidisciplinary approach in the biodomain. His academic integrity is evident through his extensive publication record that include more than 300 Scopus Index research article and 45 paper having a high H index. Notably, he has been recognized in Stanford University top 2% scientist list for the consecutive year 2022, 2023 and 2024. Dr. Pal has established research collaboration with several labs within the outside India, including the Indian Institute of Technology, Jodhpur, Seoul National University, South Korea, King Saud University, Saudi Arabia, University of Philippines, Los Banos. As the principal investigator, Dr. Pal has secured 9 sponsored research grants in India. His recent achievement including securing a bilateral grant titled Development of Composite Optic Device employing an artificial intelligence algorithm for evaluating the shelf life of raw agricultural product from the Department of Science and Technology, International Cooperation Division, Government of India. In collaboration with the Department of Science and Technology, Philippines, additionally, Dr. Pal obtained another significant grant titled Developing an Artificial Intelligence Enabled Multispectral Reflectance Photography Device for the prediction of shelf life of bakery product from the Science and Engineering Research Broad Care Research Grant, Government of India. The title of presentation will be the development of multifunctional optical device for the process monitoring application. So we are highly fortunate to invite our keynote speaker, Dr. Kunal Pal sir, at this FDP session. Thank you, sir, and stage is yours, sir.
So it was truly an honor that you accepted our invitation. So the stage is yours, sir.
Yeah, thank you, no, Professor Vanesh, and thank you other faculty members and the organizing committee who have been associated with this workshop. It's truly an honor to give a presentation and share what we are doing at our lab at NIT Rourkela with you guys. Okay, so I would especially like to thank Dr. Uvanesh for inviting me. So he gave me a call and he was telling that there is no fund for us. No, that's not a problem. As a researcher, it is always our lookout how we can share our knowledge, and I am happy to share my knowledge with the young minds because what I believe is that uh, sharing when if I share the knowledge, so the knowledge will be percolated to a mass, and maybe from a single word or single say line what I speak, it may open up a new research area domain for the listeners. Okay, I would give my uh, one example. What happened is that one of my student, PhD students, I asked him. In fact, he was the classmate of Dr. Vanesh, and I asked him to visit 4 or 5 workshops across the India. He also went abroad for one conference. So from those 4 or 5 workshops, out from 2 or 3, he got single word from those workshops. Okay, it was all say 4 or 5 days workshop, but he got some keywords which are the buzzwords and that on that topic people were working. So using those 3 or 4 keywords, he shaped his PhD career and he is now doing well. He is running one company. So he has started his entrepreneurship business. So like that, there are several other examples where I always ask students to to go to various workshops and listen to what others are speaking, what others are doing, because the what say whatever I am doing, maybe that facility is present to for you also, but you are not able to extract the information from there. When I speak to you and when I will demonstrating my results, it might so happen that you will get an idea that okay, we can represent this data in that way also. Okay, so it opens up a broad perspective in the minds of the listeners or the researchers. Okay, so with this short talk, I will start my this presentation. Okay, share. So is my screen visible to you?
Yes, sir. Yes, sir. Yes, sir.
Okay. This is the problem. Let me- Mm, Okay. Anyhow, so good evening, everyone. So good morning, everyone. So what I will do is that I will start with my talk, and this talk would be uh, an interactive one. So if anyone of you are having any issues or you want to know anything from any specific slide, please don't hesitate to stop me, and then we can discuss about that principle or whatever doubts you are having. Okay, so today I'll be discussing about the development of multifunctional optical device for process monitoring applications. I'm sorry, this band it is not going, so I'm not finding the way to hide it, and it is not going out of the screen also. Anyway, might be uh, this Zoom they have changed their settings somewhat because previously we could hide this band. Okay. Anyhow, so as the organizing team, they have already introduced me. So I am Professor Kunal Pal, and I am working at the Department of Biotechnology and Medical Engineering at NIT Rourkela. Okay. So as you can see, you must have heard from the introduction. I basically work on many areas, including drug delivery, including biomedical, including food technology. Okay, so what is the common thing that binds my research? The common thing is the human health. Whether it is drug delivery, whether it is food science, whether it is biomedical engineering, in all the things you will see in somehow or somewhat these areas they affect the health of a human population. Okay, when we talk about the food, we need to maintain a certain degree of food quality and safety. Okay, because across the globe what happens is that every year nearly 4.2 lakhs of people they die due to foodborne illness. Okay, and uh, apart from this, there is a huge number of population who undergo morbidity, not mortality. Mortality means the death, and what I mean to say, no morbidity, where people suffer, and when people are suffering due to some illness, it also affects the GDP of the country. Okay, so due to this reason, it becomes customary to analyze the quality aspects and the food safety aspects of the food. These are some of the common quality aspects and the safety aspects that are being monitored in day-to-day life by the food regulators. Okay, so among these, the optical devices that we developed at our lab, they are more what you call they help us in analyzing these highlighted areas. That means the appearance of the food, the processing techniques of the food. Then it can help us in food fraud and detection. It can help us in analyzing the microbial biological safety of a food product, right? So apart from this, if you look into the appearance, through the appearance we can guess the freshness, we can guess the texture. And when we talk about this packaging, through packaging, what is the major, one of the major what you call this application of the packaging system, it is to stop the microbial growth. Okay, so if you see, most of the things are interrelated. So using that optical device, if you see, we are able to analyze a large number of the quality and the safety aspects related to the food. Okay, and for that person, for that reason, what we have done is that we have taken 4 parameters that we wanted to study across this whole span of quality and the safety aspects. Okay, so when we talk about this food inspection, so we can do the food inspection by various methods like chromatography, then spectrophotometry, microbiological testing, hyperspectral imaging, NIR spectroscopy, and SERS. SERS means surface enhanced Raman spectroscopy. Okay, so these are the common techniques. But if you look, most of these analytical techniques that we propose, they are either very costly or the sample preparation is very what you call tedious. Okay, similarly, if you look into the microbial biological testing, so we have to do the microbial test for at least 24 hours to get some meaningful results. So in that regard, what people are suggesting is that to reduce the time of analysis, they are going for the spectrophotometric based testing. It may be spectrophotometry, it may be hyperspectral imaging, it may be NIR spectroscopy, or it may be ACRS. Okay, so people are trying to analyze these things to reduce the time that is needed to do the microbial biological testing. But the problem is that if you look into these systems, including the spectrophotometry, which is the cheapest among all these analytical tools, so what happens is that their cost is very, very high. If you look into the spectrophotometry, it would cost, say, double beam spectrophotometry, it costs in today's date, it costs around 5 lakhs. Okay, in Indian rupees. Okay, so hyperspectral imaging, it costs around 50 lakhs. Okay, NIR spectroscopy, it costs around 30 to 40 lakhs. Okay, Raman spectroscopy, it costs around 70 lakhs. So our main aim was to determine whether we can make a low cost solution which can help us in analyzing the food products, and at the same time it will not be compromising with the quality of the analysis. Okay, so as I already told you uh, this thing, so as I already told you, these systems, they also have some limitations. So what are the limitations? The limitations include most of these analyses, they are destructive in nature. Okay, so that means if you are having a food product, you have to cut it or do some sample preparation, and you will not get back the original sample. Okay, so they are destructive in nature. And if you want to randomly check some samples whether it is contaminated or whether it is safe for consumption, and if you try to destroy mm, some products, it is a loss to the manufacturer or the retailer. So you don't want that to happen. Okay, the second thing is that it's extensive sample preparation methods, then it is labor intensive. Okay, because you have to prepare the sample and all these things, it can be time consuming. You need skilled personnel to go for the analysis, and as I already told you, most of the techniques, they are highly costly. Okay, so saying this, what are the non-destructive methods? Because if we can design one analytical method that is non-destructive in nature, so what it can do is that it can save a lot of money not only for the industrial setups, but also for the retailers who are selling the products. Okay, because we will not be destroying their food products, and that will be spared and they can sell it. So among these, some of the common things are optical imaging. Okay, second is visible spectroscopy based analysis. Then uh, next is infrared spectroscopy, and lastly it may be a mass spectrometry. In the mass spectrometry, we have to have some amount of sample which needs to be injected. So we are not uh, basically, it is not completely non-destructive, but since we are taking only a small amount, say in the milligrams, so we are taking the samples, and hence it is often classified under non-destructive methods. Okay, so what are the advantages of these spectroscopic techniques for the food safety analysis or food safety prediction? Okay, so first one is, it is having a rapid testing, then non-destructive, and lastly the environment friendly uh, method of analysis. Okay, challenges in deployment: complex instrumentation. Okay, data acquisition and analysis, it can we have to use algorithms, and we need to generate large data sets. And lastly, scaling for industrial use. As I told you, if I ask a small MSME industry to integrate a 70 lakh instrument for the analysis of the food products, they will not use it. Okay, so that is the main problem. Okay, then coming to the recent advancements with the development in the field of sensor integration, sorry, in the field of sensor integration, data processing, and real-time monitoring systems, it is now possible to develop or implement these complex systems in the food industries, and that too at a low cost. Okay, so what are the research gap? The research gap includes the lack of multiple parameters, uh, monitoring of the multiple parameters simultaneously. Okay, then miniaturization and portability. So we need to miniaturize the product so that they can be applied for on-site application. Then next is integration of AI-driven analysis, because when we integrate this AI-driven analysis, it increases the chances of positive prediction, and it reduces the chances of false prediction. Okay, and lastly, cost effective. When we integrate these AI-driven systems to with the low cost systems, it can give us cost effective solution. Okay, so herein what solutions we are providing, what we try to do is that we try to take the color information, spectral information, and hyperspectral information, and we try to develop an instrument which is capable of collecting all these three information, and then we try to integrate our AI models with that, so that we should be able to get uh, get automated analysis and detection of the sample. Okay, so for that purpose, we went for these 5 objectives. So initially, we developed a standalone multimode colorimeter for process monitoring applications. So then what we did is that upgradation of the colorimeter to spectrometer. Okay, for non-invasive spoilage monitoring using machine learning models. Okay, so what we have done is that we have taken the spectrometer, we have converted this colorimeter to the spectrometer, and it is quite interesting topic, because when we talk about the colorimeter, we use imaging sensors where we are having only RGB planes. Okay, so when we talk about the spectrum, we are having in the visible spectrum, we are having 400 to 100 nanometer wavelength. Okay, so out of this, we are having only three wavelengths. Okay, red is at around, say, 780, green is somewhere around 650, and In blue region, it is around 400 or 450, wherever you want to take. So out of this full wavelength spectrum, in RGB cameras, we are having only 3 wavelengths. Okay, we are having only 3 wavelengths. So from there, how we got the full wavelength spectrum, I will be discussing with you with that. Okay, then after we developed this spectrometer, we developed deep learning framework using the digital images that were captured using the colorimeter cum spectrometer for non-invasive foliage monitoring. Okay, then we upgraded this spectrometer into a hyperspectral imaging system. Okay, into a hyperspectral imaging system. Okay, and then lastly, we did the integration of optimized AI models into a unified platform. Okay, so that means we took the uh, this colorimeter information, we took this deep learning information from the images that we captured, so simple image processing. Then we used this hyperspectral images. That means the images add the different wavelengths for the detection, and then we developed an integrated platform over there. Okay, so this is the total workflow that was carried out. Okay, I'm not going into the detail, I have already told you in brief, but we are expecting in this presentation. So first one is the development of a standalone multimode colorimeter. So we developed a device. So this is the device over here. So we have an imaging sensor inside it, and this is the sample that we wanted to analyze. And herein we were not only analyze the color parameters, but we are also looking into the uh, this temperature based crystallization process, and we are monitoring the uh, process from there. And then we if you see over here, we are getting information L star and temperature, which is analog to the heat flow and the temperature that we get from the DSC machines. Okay, so which is highly costly in today's date. It would cost approximately 30 lakh rupees. Okay, so then we tried to correlate both this data, and we wanted to find out whether our system is capable of identifying critical thermal events. Okay, and that too using a very low cost solution. Okay, because if you see over here, if I ask many of you that can you buy a 30 lakh equipment, it will be very difficult for you to buy a procure a 30 lakh equipment using the government funding. And also the government funding is very it goes through a very hard selection process, and not many of the researchers, they get the funding to procure high cost equipments. Okay, so lastly, what we did, once we analyzed this and once we saw, yeah, our device can be used, we tested butter sample to analyze the crystallization process uh, in the molten butter. Okay, so this is the device. If you see, we are having a thermal sensor. Okay, over this is a spacer which will guide the light, and it will also help us in capturing the images. Okay, so here is the sample platform. So it is a sliding platform. Okay, and this is the software that we developed. Okay, so the device was made IoT enabled, so that if I want to incorporate this, suppose I want to analyze the crystallization process in a controlled environment, I can put it into the controlled chamber, and through the IoT, I can get the result outside, and I can analyze the results from outside without disturbing the sample. Okay. So how this system works? So first we have, so these are the images from the original system. So if you see, we are having a black card first, and then we are having this white placard. So first we have to do black and white calibration. So first we need to do the black calibration. We will put a black object standard object, then we will take the reading from the region of interest. We do not take all the image, we just take a small part. Okay, so we take the region of interest and select the region of interest, and from there we calibrate the image for the back calibration. Then we go for the sensor calibration for the white calibration. Okay, and once it is completed, once the calibration of the sensor is done, then we have two types of this what you call two types of modes in which the device can be operated. The first one is the quality testing mode, and the second one is the process monitoring mode. In the quality testing mode, you can bring different samples and you can analyze the samples one by one. Okay, and in the process monitoring mode, once you start the analysis, it will record the results for a particular period of time as per the details that you have given to the GUI. Okay, in this B section, if you see, we have put a different colored placard. After the calibration was done, we selected the quality testing mode. This placard was put in, and then we tested the sample, and here we get the perceived color. Now if you see, both the actual placard and the perceived color, they are having the similar color information, and all the color parameters in the RGB plane, CMY plane, HSI plane, and CIE lab plane, they have been computed for this perceived color. Okay, now this color informations can be used by the paint industry, by the textile industry, by the say food industry in analyzing or characterizing the samples. Okay, then coming to the process monitoring mode. In the process monitoring mode, see, we are having a specific uh, thing over here. So in the process monitoring mode, we have to give the process time for how long the instrument should run. The second is time interval, at what interval the instrument should take the reading. And since we were interested in capturing or capturing the thermal event based readings, we had a start temperature. So it is the temperature after achieving which the device will start recording the data. Okay, so from here, if you see, we got the intensity versus the time plot, but once we get the data, we can extract the time versus color parameters and data. Okay, so initially what we did is that we once we developed the device, we tried to analyze the device whether it is performing well or not. So we generated some color placards having definite color parameters. Okay, and this is the image of those placards. Okay, those colors. Then we acquired the data from a commercial device and from our developed device. Okay, so what happens is that if you see delta E, delta is nothing but the difference in the color information between the original placard and the color information obtained from the respective devices. Okay, so over here, if you see, in the delta E value, in all of our cases, it was much lower than the commercial device. Okay, if you see, in the first case, in the case of red, our device gave a delta E of 3.33, whereas in the case of the commercial device, it was 48.32. Similarly, for the yellow, for the commercial device, it was 16.58. Okay, now as per the literature, what happens is that if the delta E, it is lesser than 5, then you will not be able to analyze whether there is a visual change or not. Okay, so any values having delta E or any placards having delta E greater than less than 5, we will not be able to perceive that change visually, and up to 10 delta value, it is quite accepted in the food industry. Okay, so in most of our cases, if you see, uh, in many cases it was less than 5, and in some cases it was within the limit of 10. Okay, so that's why, if you see, the device that we developed, it can be regarded as that it can be used for the product quality analysis purpose. Okay, so then, as I told you, we went for the analysis of process monitoring analysis of the these oleogen samples that which are basically the food samples, and we wanted to see the crystallization processes. So we looked into the crystallization processes at three temperatures: 5 degrees, 15 degree, and 25 degrees centigrade. So if you see, in all the curves you will be getting box 1 and box 2. These box 1 and box 2 are nothing but the thermal events that are occurring in the oleogels while it is being characterized, okay, or it is going undergoing crystallization process. So similarly, we went for this DSC analysis using the costly equipment. Okay, and once we have done that, we went for the this Spearman correlation analysis. So this was the DSC data and the proposed device data, and we went for the correlation, Spearman correlation analysis. In, if you see, except this one, in most of the cases we had a moderate positive correlation. Okay, so from here we can say that the device that we have developed, it can provide us information about the thermal events of fat based products. Okay, then, as I told you, we went for the analysis of the samples, butter sample. And over here also, if you see, there are two endothermic peaks, and corresponding to these endothermic peaks, we got thermal events recorded at this region. So L star versus the temperature, we got this box 1 and box 2, which corresponded with the thermal events that we got in from the DSC thermogram. So this suggests that both the devices, again, they are capable to analyze the crystallization events in the butter sample. So we expect that it will also be helpful in analyzing these type of crystallization events, say for an example of ice cream or chocolates in the other samples also. Okay, so the summary from here is that we were able to successfully develop a dual operating mode system. Okay, so our system, it outperformed the commercial device in terms of the color accuracy. Okay, then we were able to analyze the crystallization kinetics of the oleogels, and the results were somewhat similar with that of the results that we obtain, thermal events that we obtain from the differential scanning calorimeter. Okay, now the problem with this system was we were not able to perform the spectral analysis over here. So that is the main thing. And the second thing is that over here in this first stage, we just had a fixed ROI, but in the next stage, what we tried to do is that we wanted to uh, include a dynamic ROI selection. The reason being, when we analyze the system, and being a say a material scientist by training, so I always looked into the thing is that when we were characterizing any sample through the imaging technique, we found that our area of interest was at a particular location. Okay, but we were not able to do the analysis. So that training came into my mind, and that expertise came uh, helped us in what you call in nucleating the idea that we need a dynamic ROI region selection, so that we the researchers can determine or capture the data from the specific area of interest. Okay, so the first paper, it was published, and then we had one utility patent and one design patent from these things, from this first chapter. Then we went for the upgradation of the colorimeter to an imaging spectrometer. So what we did is that we had these color spaces. So we had this imaging spectrometer. Okay. Now this imaging spectrometer, as I already told you, this is basically an imaging system, and we only have RGB values. So we developed one ANN model, and that ANN model, it was used to convert these RGB values to a spectral value. And correspondingly, what we did is that we also went for the shelf life analysis of the breed samples over a period of time, and we recorded both the RGB values and the we also performed the microbial analysis and went for the microbial count thing. Okay. Then from there, using these two information, we developed a machine learning platform to detect the spoilage in the bread samples. Okay. So we took the samples, then we incubated. Okay. At 37 degrees centigrade, and this is the flow chart. On the right we have the flow chart for the what we did. We first developed this RGB to our reflectance conversion, then through the shelf life analysis we collected this data. Okay. So color and spectral acquisition was also being performed, and lastly we went for the ML modeling. Okay. So this is the setup that we developed, because we are now integrating ML models. So we needed a better computing platform. So we upgraded the system so that it becomes an this computer operated system. So from here we this is the modified software, okay, of the device, and you will get the similar thing. However, what you will get is that herein we are having an additional spectral values. Over here we are not, we did not show all the values because it was getting quite cumbersome. And apart from that, this if you see this color, perceived color, and the color model parameters, whatever we discussed in the first chapter or the first part, they have been shown over here also. Okay. So then, as I told you, we developed a methodology for converting the RGB values into the ANN values. So what we did is that we took Pantone matching system color chart, and we generated 983 color patches. And for these 983 color patches, we collected the RGB information through our developed device. And parallelly, what we did is that we collected the spectral information from a commercially available spectral sensor. Okay. And from there, we uh, developed an ANN model. Okay. So here we developed the ANN model by applying this hyperparameter tuning using random search method. Okay. And once the ANN model was tested, we randomly selected 50 patches from the Munsell color chart. So there are two charts. If you see the Pantone matching system, and we have this Munsell color chart. These two charts or the color chart systems, they are very commonly used in color industry. It may be the paint industry, it may be the food color industry, wherever you go. And we selected separate color charts for training and testing, because we didn't want to have a overlap of the color information. Okay. And then from there we collected the reference spectra from the sensor, commercially available sensor, and we went for the this predicted spectra, which we developed from the ANN model. And then we use this information and compared it through the Spearman correlation. So from there, uh, we after we were quite confident that our device is working properly and it is generating a good quality spectra, we went for the model deployment and we integrated it to the developed software. Okay. So these are the RGB to reflectance conversion. Some results are there. So I'm not going into the details of this. So this is the ANN model architecture that we developed and the parameters that we have used. Okay. So this was the ML modeling workflow. So for the spoilage monitoring, okay. So we collected the data, RGB and the spectral data. Then we went for the data pre-processing. Then we went for the model development and evaluation. For this purpose, we went for the 3 selected supervised learning models and 3 ensemble learning models we have gone. And after training these 6 models, we went for the classification purpose. How the data was collected? As I already showed, the bread samples were taken and they were kept in a sterile container. Then they were kept at this 30 degrees centigrade plus minus 1 degree centigrade, and the readings were taken for 10 days at 48 hours interval. And lastly, we went for the color and the spectral data acquisition. So from here, after the collection of the data, so we went for the feature selection method to reduce the dimensionality of the data, and for that we used the forward selection method. Okay, and for this forward selection method, we again use the 6 ML models that we have selected previously. Okay, so from here, after the feature selection, we got that 5 color parameters and 22 spectral parameters. They might be sufficient enough to represent the whole data set. And these 5 and 22 spectral color information we got from the GBT and from the GBT model. Okay, so if you see, GBT model gave 27 parameters, 5 plus 22, whereas XGB parameter, it came up with the same F1 score, but over there we had 48 selected features. Okay, since GBT was having the lower number of the features, so we selected these 27 features for the training and testing. So the data this was the new data set. Okay, so which were having 27 features, and from there we went for the 2-class distribution. In the 2-class distribution, the samples were classed into fresh and the spoiled, and in the 3-class distribution we went for the fresh, marginally fresh, and the spoiled data based on the microbiological data that we obtained. Okay, so then we went for the 5-fold cross validation of the 5-fold cross validation during the training purpose to improve the generalizability. And then we went for the model hyper training, and then again the testing and the validation of the results. Okay. So herein, this is the sensor data analysis. In all the cases, if we see, we got very strong positive correlation and strong positive correlation among the predicted and the estimated results. Okay, the black line, it is the predicted one, and the red dashed line, these are the standard or the reference spectra that we obtain from the this color, these spectral sensors. Okay, so then we collected all this information and all these things. If you see during the spoilage season, over here there has been a significant change in the uh, data, this data as the day progressed. Okay, so this is the shelf life analysis. So this is how we classified the uh, these data sets. D1 means 2-class systems and D2 means 3-class systems. Okay, so this was all based on this microbiological data that we obtained. Okay, so again we distributed the data in this way, and then this is the ML modeling flowchart for the pipelining that we employed. So over here, if you see in the D1, what we were having in the training and the validation, GBT, it gave us the best result. However, if you see in testing, we got SVM as the best result. Okay. Similarly, in D2 also, GBT gave very good results in the training and the testing. However, for the testing, we got SVM as the best model. Okay. So from there, we generated the confusion matrix for the testing value. So over here, if you see the SVM, it gave us the best result. Okay. So summary. So we developed a CMOS camera based spectrometer wherein we did not need any what you call spectral lenses or the filters to acquire the data, and inclusion of those systems would have increased the cost of the device. So we were able to get rid of the costly optics that are being employed in the spectrometers. Okay, so this study was published in the journal Food Chemistry with an impact factor of 9.8. And over here again, there was a scope for improvement. We can do the image based analysis, and for the image based analysis, we can either include deep learning or transformer learning approaches. Okay, so accordingly we did that. We got the data collection. Initially we took the color and the spectral components. Herein we only took the images. Okay, and we employed the 2D CNN and transformer learning models for the estimation purpose. So I am not going into the detail because the methodology basically remains similar. Okay, so I am directly going to the this classification this thing. So if you see the F1 score for D1 in the testing phase for for training and validation, it was 99 and 97% for the inception weight 3. But in the testing, we got that 2D CNN it performed better. Similarly, in the D2 class, where there were 3 class systems, we got 90% accuracy in the testing phase using the 2D CNN that we developed. Okay. So these are the this confusion matrix, and 2D CNN, we can see it performed the best. So we have submitted this paper, and we are it is under review. So uh, that's it. So where is the scope of improvement? Over here we used only the digital images. Okay, however, spectral images, that means the hyperspectral images, can be used for this purpose. Okay, so till now what we were having, from RGB we got spectral information. Okay, now say from 400 to 800 we are having this value. Now from where we got this, we selected an ROI, and from there we got the RGB values, and by putting this RGB values we computed this spectra. Okay, now what do you mean by hyperspectral images? Can anyone tell me? No? Okay, so what we have basically in an image, we'll be having a large number of pixels. Now what are these pixels? So I'm not going, so like this it will be there. So what are these pixels? Each pixel, it will be having an RGB data. So can we not convert these RGB pixels for each pixels into the spectral information? Now, if you see, if I make some ghost image of different images, say the first one is now say 400, the second one is 450, the third one is 500, and so on. For each pixel, what we are getting? We are getting the spectral values. Now I have to just put in the values. What is the spectral intensity at 400 to the 400 ghost image? Then if I go to the say 450 spectral component, what is the image? In the first ghost pixel for which from which we have computed this spectra, we can put in this value in the second image. Similarly, if you go for the 500 wavelength, nanometer wavelength, we will be getting an intensity, and that intensity can be plotted over here. So if we go for each of the pixels, measurement for each of the pixels, you will be getting the hyperspectral images. You will be getting an images for 400 nanometer, for 450 nanometer, for 500 nanometer, and that way, right? So in this way, when you are doing this, so you are creating images that are of different wavelengths using a single RGB image, Okay, so that means using any CMOS camera or any color camera, you will be able to generate hyperspectral images in the visible range. Okay. So that was our funda, and based on that, we went for the upgradation of the spectrometer into a hyperspectral imaging system, and this is what it has been given. So we use that 2D CNN and the inception model and the other this transform learning models for the classification. But instead of just using the image, normal image, color image, we used the hyperspectral images. Okay, and in the first case, if you see, we try to find out in the spectrometer case, we try to find out the what are the wavelengths. Okay, in this case, we perform the wavelength selection using two methods. One is manual method, wherein by looking into the spectra, we just identified the important spectra, this wavelength points, and we used it. And in the second one, we used an automatic method. We used this model selection methods to calculate this spectral, to find out the spectral values, which can give us very good results. Okay, and the rest of the things, data acquisition, it remains similar. Okay, so this was the modified thing where we get the hyperspectral info. We can get the spectral images also from there, and from there we can also generate the hypercube. Okay, so this is what I try to make you understand. Okay, the spectral images. So data collection, I already told you it was similar. So I am directly going into the results. Again, yeah, feature selection. Here the feature selection, it was the forward selection method we have used. Okay, and uh, we have used the spectral information over here for the yeah, auto wavelength selection. Okay, so from there we selected this manually selected wavelengths and the auto selected wavelengths. Its data, it is given over here. Okay, so these are the spectral thing. So from here, if you see how we selected the data points, it's there. This is the model, this manual method. Then over here we went for this generation of the hyperspectral images at this manually selected wavelength and auto selected wavelengths, right? Then we have this data set distribution. Okay, so let's go for the accuracy. In the accuracy, if you see in the testing, we have ResNet 50 as the better model, and in the D2 this thing we had this Inception V3 as the best model. Okay, so ResNet 50 for the D1 class and Inception V3 for the predicted class, for the D2 class dataset. Okay. Similarly, for the this auto wavelength selection, we get 2D CNN and Inception V3 for D1 and D2 respectively. Okay, so these are the key findings. So we are in the process of communicating this for the project, for the publication, and we expect that that in the couple of weeks time we should be able to submit this project, submit the paper to the to the journal. Okay, so real time, then we went for the real time testing. So this is what it looks like before testing. So herein we have basically developed an unified software, and we tried, we integrated the best performing ML and the DL model. And after testing, if you see the prediction panel, it will give you in the D1 class, as for the D1 class, whether you are having the fresh or spoiled. Similarly in D2, whether you are having it as fresh or spoiled. From the normal images, again, the D1 image, it says spoiled, whereas D2 image, it says likely spoiled. and the hyperspectral images we are having D1 and D2 fresh and likely spoiled. Okay, so in this way and these are the testing classification results. Okay, so overall conclusion, we were able to develop a multimode colorimeter cum spectrometer cum snapshot hyperspectral imaging system. We were able to develop some machine learning models that can be integrated with the device, and these low cost devices, they can be used for what you call for the spoilage monitoring purpose. Okay, shortcomings. Uh, Limited ANN color training because of the limitation of the color chart. We can in future we can increase the color training database. Then over here we just used bread as the validation model. So we had restricted food system validation because within 5 years you can do a minimal amount of thing. So then we have only done the lab level validation, and the CMOS sensor that we have used, it is just a 5 megapixel camera. So if we increase the camera size, we may go for we may get better results in future. And lastly, poor model interpretability. Some people may find it very difficult to interpret the results if proper training are not given. So we are working on that, how we can reduce the interpretability of the results. So the in-house developed this computer control spectrophotometer. It would cost somewhere around 20,000. If you want to try to develop the spectrophotometer in the standalone mode, it can cost around 60,000. And in-house developed spectrophotometer come hyperspectral imaging system, it would cost you around 80 to 1 lakh rupees. Okay, uh, for the developmental purpose. So uh, in this way we can see that by uh, understanding some basic phenomenon, we will be able to develop some systems that can be used in our labs. Okay, so these are some of our notable collaborators. Okay, so some of our notable international collaborators are here. Okay, so this is our YouTube channel. We post about our research, what we are doing in our lab over here. So thank you very much. If you have any question, we will be happy to, I will be happy to answer those.
Gaurav sir,
Yes, I have given access
access.
to all the participants. They can unmute themselves.
हाँ.
Yes.
हेलो.
Yes, sir.
हाँ सर, नमस्कार सर.
Namaste.
सर नाइस लेक्चर. सर मैं एक चीज समझ नहीं सका कि आप क्रिस्टलिनिटी देख रहे थे बटर में एंड ऑयल्स में ऑल्सो. वहाँ एक स्लाइड है जहाँ पे आपने इनिशियली दिखाया सनफ्लावर या राइस ब्रान ऑयल के बारे में.
हाँ जी, हाँ
तो
जी.
मैं सर एक चीज नहीं समझ सक रहा हूँ. वहाँ पे आप एक्चुअली देख क्या रहे हैं? जैसे कि हमने मार्केट से एक तेल खरीद के लाया,
हम्म
तो उसमें अगर एक तेल एक्सपायर डेट है और एक विदाउट एक्सपायर्ड है, तो हम तो हमें तो कुछ समझ में नहीं आएगा. तो इसके लिए ये मशीन है कि ये मशीन हमें बता देगा कि ये एक्सपायर्ड के बाद क्या हो रहा है, क्या नहीं हो रहा है. तो ये जो आपने समझाया हमें, इतने साइंटिफिक आपका फील्ड फूड केमिस्ट्री में जितने सारे इंस्ट्रूमेंट एंड दैट डाटा, एक्चुअली नॉर्मल मैन अगर समझ में चाहे तो कैसे समझे सर? थोड़ा बताएंगे प्लीज.
हाँ, हाँ देखिए, यहाँ पे क्या हो रहा है, मैं फिर से आपको शेयर करता हूँ स्क्रीन.
हाँ प्लीज सर, प्लीज.
यहाँ पे जो हम ये बोले हैं, यहाँ पे देखिए राइस ब्रान ऑयल, कैंडिलिला वैक्स एंड सनफ्लावर लेसिथिन से हमने एक ओलियो जेल बनाया. ओलियो जेल क्या है? ओलियो जेल है जैसे आपका ऑइंटमेंट देखे होंगे, बटर
या
देखे होंगे, या फिर घी देखे होंगे. तो
हाँ
घी में
हाँ
क्या हो रहा है, आप अगर उसको हीट करते हैं तो हीट करने से वो ट्रांसपेरेंट हो जाता है, राइट.
या
जब आप
यस
उसको
सर,
कूल करना शुरू करते हैं, वो फिर पहले आपका वो
सॉलिडिफाई हो जाता
क्लाउडी सोल्यूशन होता है,
है.
ठीक
या
है. फिर वो
या
क्लाउडीनेस बढ़ता बढ़ता जाता है। उसमें क्या हो रहा है, उसमें जो हो रहा है, जो सॉलिड फैट्स हैं, सॉलिड
स्टडी
फैट्स वो आपका प्रेसिपिटेट आउट हो रहे हैं सोल्यूशन फॉर्म से, एंड देन वो सॉलिड फैट्स वो नेटवर्क फॉर्म करके एक सॉलिड स्ट्रक्चर बना रहा है, राइट।
या
द ओलियोजेल्स, इसमें क्या है, यहाँ पे ये ओलियोजेल्स इनको कंसिडर किया जाता है कि ये ओलियोजेल्स आर बेटर ऑल्टरनेटिव टू द बटर और द घी, क्योंकि घी और बटर में आपका सैचुरेटेड फैट है। तो इसलिए लोग
ओके
क्या ये कर रहे हैं, दे आर गोइंग टूवर्ड्स द बटर और घी ऑल्टरनेटिव। और यहाँ पे आप अगर देखेंगे, इसमें कैंडिलेला वैक्स जो है, जो सैचुरेटेड फैट है, इट इज ओनली 5%, बट इन बटर एंड
ओके
घी इट इज अराउंड 70 to 80%। ठीक है, लेकिन इसमें क्या ये है, प्रॉब्लम क्या है, आप इतना कम सैचुरेटेड फैट से आप इसको बना रहे हैं, तो इसका प्रॉपर्टी तो अलग हो जाएगा
यस
ये बटर और घी से। और
यस
हमारे मुंह में देखिए, अगर आप नॉर्मल तेल आपके जस्ट आपके टंग में लेंगे, उसका कोई टेस्ट नहीं है।
नहीं है या
टेस्ट किसका आता है, टेस्ट आता है ये सॉलिड फैट जब ये होता है, मेल्ट होता है, वो हमें एक फीलिंग देता है।
या
ओके, वो हमें
हाँ
एक फीलिंग देता है, और हम उसको बोलते हैं टेक्सचर। ओके, इन
यस
फूड साइंस में हम उसको बोलते हैं टेक्सचर। वो
ओके
टेक्सचर से ये करके आप एक आइसक्रीम को पसंद कर भी सकते हैं, नहीं भी कर सकते, ये कोई फैट बेस्ड सिस्टम को पसंद कर सकते हैं, नहीं कर सकते। एक मैं आपको सिंपल एग्जांपल दूंगा। इसका एक
यस
कॉमन
सर
एग्जांपल है आपका, जो फ्रोजन डेजर्ट्स आता है और अमूल का जो ये आता है, अगर आप फ्रोजन डेजर्ट किसी लोकल कंपनी से खरीदेंगे, उसमें आप देखेंगे कि उसका टेस्ट आपको अच्छा नहीं लग रहा है, लेकिन इंग्रेडिएंट तो सब सेम है ना। इसका मतलब है
या
जो फैट जो क्रिस्टलाइज किया है वहां पे, वो ठीक ढंग से नहीं किया होगा, क्योंकि प्रिपरेशन कंडीशन में वो प्रिपरेशन कंडीशन ठीक से मेंटेन नहीं किया गया होगा। ठीक है,
या
लेकिन फ्रोजन डेजर्ट अगर आप ये क्रीम बेल का लेंगे और अमूल का लेंगे, क्रीम बेल भी एक अच्छा कंपनी है, अमूल भी एक अच्छा कंपनी है, दोनों का लेके आप टेस्ट करेंगे, आपको वो पता नहीं चलेगा। अमूल इज फुल क्रीम, उसको आइसक्रीम बोलते हैं, फ्रोजन डेजर्ट नहीं बोलते हैं, राइट। इसको लेके
हम्म
बीच में आपका काफी हंगामा भी हुआ था, 1 1.5 साल 2 साल पहले। अमूल ने उनके ऊपर केस किया था, बाकी सब आइसक्रीम मैन्युफैक्चरर्स के ऊपर, कि आप उसको आइसक्रीम नहीं बोल सकते, क्योंकि आप उसमें क्रीम नहीं डाल रहे हो, विच इज बेसिकली सैचुरेटेड फैट, जिसमें सैचुरेटेड फैट है। तो इसमें आप क्यों नहीं कर पा रहे हो, इसमें आप क्यों इसलिए नहीं कर पा रहे हो कि फ्रोजन डिजर्ट में आप ये क्रीम का ऑल्टरनेटिव डाल रहे हो, लेकिन वो एक टेक्सचर दे रहा है विच इज सिमिलर टू द क्रीम, एंड ड्यू टू दैट रीजन दोनों का जो आप फ्रोजन डेजर्ट और आइसक्रीम खाएंगे, आपको उसमें फर्क नहीं पता चलेगा। तो हम लोग एज ए फूड साइंटिस्ट, जब हम उसे एनालाइज करना चाहते हैं, तो उसमें उसका क्रिस्टलाइजेशन कैसे हुआ नहीं हुआ, वो कैसे पता लगाएंगे। वो हम लोग फिर इस मेथड से जाते हैं कि जैसे यहाँ पे देखिए हमारा टेम्परेचर है, और एल स्टार वैल्यू वो एक कलर पैरामीटर है। हम उसको जब कूलिंग कर रहे हैं, वो किस हिसाब से वो आपका क्रिस्टलाइज कर रहा है, और उसका ये जो पैरामीटर जो है, ये जो प्रोफाइल जो है, वो कैसा बन रहा है, उसके ऊपर हमारा वो टेक्सचर बनेगा।
यस सर
समझ में आया आपको?
यस सर बहुत बढ़िया से आपने समझाया
हाँ,
सर।
ठीक।
मगर मेरा ये क्वेरी है कि जब एक बटर, तो वो बटर विथ
आपका वॉइस ब्रेक हो जा रहा है।
एक्सपायरी डेट की बात होता क्या है?
एक्सपायरी डेट के बाद होता क्या है, वो
हाँ
आपका
दोनों में
ऑक्सीडेशन
अंतर
होता
क्या
रहता है।
है? ये नहीं नहीं मैं क्या बोल रहा हूँ, देखिए सर उसको हमने फ्रिज में रखा, राइट?
हाँ।
उसको हमने फ्रिज में रखा
हम्म।
और उन्होंने एक एक्सपायरी डेट डाल दिया है कि ये इतने में एक्सपायर्ड हो जाएगा एग्जैक्टली सर। ये
हम्म।
प्रैक्टिकली मैं आपसे पूछ रहा हूँ, हाँ मुझे ये जानना है एक्चुअली कि आप काम करते हैं इस एरिया में, तो ये बहुत आई फील सबके लिए इंपॉर्टेंट होगा कि एक फूड आइटम है जो बटर है, बटर का एक एक्सपायरी डेट है और
हम्म।
हमने फ्रिज में रखा, अगर नहीं खा रहे हैं वो एक्सपायर्ड हो गया,
हम्म।
तो एक फेस अगर लाएंगे और उस एक्सपर्ट के साथ कंपेयर करेंगे तो हमें क्या डिफरेंस मिलेगा? उसमें क्या माइक्रोबियल ग्रोथ हो जाता है, या जो
हम्म।
जो उसमें फैटी एसिड्स है, राइट, जो एसेंशियल और जो है वो टूट ब्रेक डाउन हो जाता है, या क्या होता है? क्योंकि हमने तो उसको कंडीशन मेंटेन करके रखा है एग्जैक्टली, यू अंडरस्टैंड नो सर?
हाँ, नहीं
होगा
नहीं,
क्या?
वो सही बात है। आप
हाँ क्या होगा
आप
एक्चुअली?
देखिए।
आपने कभी ऐसे काम किया है सर, उसमें स्टडी किया है क्या? आप करते होंगे तो मैं इसीलिए पूछ रहा हूँ,
देखिए,
प्लीज सर।
जैसे आप तेल के बारे में बोल रहे हैं, तेल में पानी नहीं है ज्यादा, उसमें है ही नहीं
या
पानी। ब्रेड में क्या है,
यस
आपका
सर।
पानी है, इसलिए आपका माइक्रो ग्रो कर सकता है। तेल में क्या है, तेल में आपका है फैटी एसिड्स है, कुछ
हाँ,
सैचुरेटेड फैटी एसिड्स है, कुछ अनसैचुरेटेड फैटी एसिड्स है।
अनसैचुरेटेड फैटी एसिड से,
एंड
यस।
अनसैचुरेटेड फैटी एसिड का क्या हो सकता है, ऑक्सीडेशन हो सकता है। क्लास 11 12 का बेसिक जो नॉलेज है हम
हाँ
लोगों के
सर,
पास,
यस
एन
सर,
सैचुरेशन है तो उसमें ऑक्सीडेशन प्रोन है। तो
यस सर।
ऑक्सीडेशन प्रोन है तो वो जब आप रखते हैं, आप जितना
हम्म।
भी स्टेबिलाईजर लगाइए, कुछ भी लगाइए, वो धीरे धीरे ऑक्सीडेशन तो होता रहेगा। तो धीरे
ओके।
धीरे एक्सपायरी के बाद उसका ऑक्सीडेशन हो जाता है प्रीडोमिनेटली तेल में।
अच्छा।
ठीक।
अच्छा, आई मीन टू से कि नहीं सर, आपने कभी ये ऐसे अगर काम अगर प्रेजेंट करें ना, बहुत बढ़िया लगेगा सर। रिक्वेस्ट
हमने नहीं
करते हैं
किया,
कि
ये
ऐसे
ये सब बेसिक चीजें हैं जो कि आपका काम ऑलरेडी हुआ पड़ा हुआ है।
ओके ओके ओके
हाँ
ओके ओके,
हाँ
हमने तो
हाँ,
एरिया नहीं
आप
है ना
नया
सर, हमें
नया
ये एक्चुअली।
पर्सपेक्टिव आप दे सकते हैं, आप जो बोल रहे हैं वो भी
हाँ,
सही बात है,
या
तो वो कर सकते हैं।
क्योंकि सर, क्योंकि
हाँ,
सर देखिए
लेकिन
ब्रेड
उससे
जो
फिर
होता है
वो
ना।
पीएचडी का थीसिस नहीं निकलेगा ना।
ना ना, नो नो सर, ठीक है। सर जो
हाँ
ब्रेड है ना, ब्रेड
हाँ जी।
एक्सपायर डेट के बाद भी एक दो दिन के बाद भी आदमी फ्रिज में रख के खाता है।
हाँ, आपका
इट मीन
ब्रेड का
सेम
कितना
खाता
दिन
है।
का आता है, ये हमने तो कमर्शियल ब्रेड लेके किया है। आपका
हाँ
ब्रेड का जो एक्सपायरी डेट आता है 5 दिन का मैक्सिमम रहता है।
हाँ,
हमारे यहाँ
रहता
से
है ये
देखिए
सर।
वो 6 दिन के बाद से वो न- मतलब अर्ली स्पॉइलेज का ये दिखा रहा है, साइन दिखा रहा है
दिखा रहा है ये। हाँ।
अर्ली स्पॉइलेज का। तो अब
हम्म,
मतलब जब माइक्रोबियल कम काउंट कम है,
हम्म।
तब भी आप खाना खा सकते हैं। मैं आपको एक अच्छा एग्जांपल दूंगा। आप नॉर्थ इंडिया से है क्या?
नहीं सर, आपका उड़ीसा से हूँ सर
उड़ीसा
मैं।
से? अच्छा,
कॉल
ठीक है।
कर, हाँ।
हाँ ठीक है। तो आप जब दही बनाते हैं
हाँ,
गर्मी के दिन में, अगर आप दही को अगर 2 3 दिन एक्स्ट्रा रख दोगे तो क्या होगा?
या ये सर अंडरस्टैंडिंग, या स्मेल करता है और ग्रोथ ज्यादा हो
बहुत
जाता है
ज्यादा
सर
खट्टा
उसका।
हो जाता है ना?
हाँ हाँ सर,
तो
हाँ।
वो उसमें वो क्यों होता है?
दैट इज बैड
वो
फॉर दैट।
क्योंकि माइक्रोबियल काउंट जो है वो बढ़ता
बहुत
रहता
हो
है।
जाता है,
हाँ हाँ।
हाँ।
लेकिन दही में भी तो माइक्रोब है,
यस
लेकिन हम लोग
यस,
उसको तब तक ले सकते हैं जब तक वो आपका
अप टू लिमिट।
विद इन
या
द लिमिट है। कंजम्पशन लिमिट के
या
अंदर जब तक है,
हाँ
तब
हाँ।
तक हम उसको ले सकते हैं। वो कंजम्पशन लिमिट से बाहर चला जाएगा तो वी कैन नॉट टेक इट।
ओके सर, थैंक यू, बहुत बढ़िया लगा सर आपसे बात करके, थैंक यू।
थैंक यू।
So actually we
Okay.
are getting late, sir.
Yes.
So sir, it was truly. Give me a moment, sir. Rakshi, sir.
Yeah. Thank you, Professor Pal, for your insightful talk on the development of biosensing devices. And it's always a pleasure to listen to a fellow Jadavpurian working in this field and doing such fantastic work. It was a pleasure to have you with us today. And
Thank you.
I want to invite Dr. Yivnesh to present this memento to Professor Kunal Pal. Please, Dr. Yivnesh.
Sir, it was a great honor to have you as a keynote speaker for our faculty development program. We sincerely appreciate your time, insight, and experience you shared with us. Sir, please accept this memento as a token of our deepest gratitude and appreciation. So it was truly an honor, sir, to have you here.
Yeah. Thank you. Thank you.
Okay.
Yeah.
Now, for the next talk, I want to hello. Am I audible?
Yes.
I'm
Please
audible.
go
Yeah,
ahead.
fine. So for since we are running like around 15 minutes late, so being delayed further, so I want to invite Dr. Roshan Kumar Hota to give his insightful talk. Dr. Roshan Kumar Hota holds a BTech, MTech, and PhD degree from IIT Kharagpur. His research areas include design of robotic hands and robotic manipulation. He is presently an assistant professor in the Mechanical Engineering Department at the Indian Institute of Technology, Jodhpur, and leads the dexterous manipulation laboratory there. So I invite Dr. Hota to to start his talk. Please, Dr. Hota, the stage is yours.
Yeah, thank you for the kind introduction. I will share my screen. So, Do you see the presentation mode?
Yes, we can see it.
Okay, fine. Just so switch in my video so that you can see this. Thank you very much for having me to deliver the talk on medical robotics. So I am Roshan Kumar Hota. I am associated with the Mechanical Engineering Department and IDRP Robotics and Mobility Systems at IIT Jodhpur. My areas of research are broadly robotics. Mainly, I have focused a lot on the areas of multi-fingered hands, grasping, and manipulation. So to start this talk, I would like to give a overview of the field of robotics. So in robotics, we focus on things that move and things that move intelligently. This could be a broad definition of the kind of activities that is done in the field of robotics. So here you see, do you see the mouse pointer?
Yes, go ahead. Yes,
Okay.
yes.
Yeah. So here you see one of the earliest forms of robots that were developed. These are industrial robots. So these robots came at around 1950s and 1960s. And after that, there was robots developed to solve many different problems. For example, we have the quadcopter flying robots, the flapping wing flying robots, or we have the underwater robots and ground vehicles, so autonomous ground vehicles. So all of these aerial robots or underwater robots or ground robots are broadly mobile robots. Generally, the industrial robots have a fixed base, but their architecture is similar to human arms. So these are also called robotic arms. And then we have on the right, you can see some examples that are more relevant for medical robotics point of view. So you have continuum robots. So this one is a continuum robot, and this is often used for surgical applications. Then you have exoskeletons, you have leg prosthetics, you have surgical robots. So all of these are used for medical robotics. Apart from that, there's also an area of swarm robots and emerging area of soft robotics. So if you look here to the industrial robot, it is mostly rigid components, but there's a lot of interest in robots with soft body structures. This is called soft robotics. So in this slide, I'm just trying to give you a overview of what you would call robots. It's not exhaustive, but some idea about what you would call robots and robotics. Next, these are the some topics that are covered under the field of medical robotics. So medical robotics itself has many different kinds of activities going on in the research community. And one prominent kind of activity is surgical robotics. Robots applied to surgeries. Then there are activities going on in the field of rehabilitation robotics. So this could be for recovery from some deformity or disability, or it could be augmentation of some abilities in which recovery is not possible. So both of these activities are done in the field of rehabilitation robotics. And then you have the area of prosthetics. So in prosthetics, generally, if one of the limbs are missing, whether hand or leg, then those are replaced by robotic devices. So it could be a hand prosthetic device or a leg prosthetic device. So uh, both of these are available commercially, and also a lot of research activities happening in these areas. And the last is social robotics. In social robotics, topics like interaction with the patient and mental well-being, sometimes catering to children with autism and other difficulties, is covered under social robotics. The main aim is to interact with the intelligent robot so that the emotional well-being and mental well-being of the patient is taken care of. So all of these areas in robotics started immediately after the first robots were made. So you can say 1950s and 1960s. Many of these areas became very prominent since the 2000s due to substantial research output in the previous years. For example, the Da Vinci surgical robot became prominent around that time. But yes, all of these areas of research have been going on since the dawn of robotics, and till today, uh, many solutions and improvements are being proposed. I'll go into each of these topics in more detail. So first is rehabilitation robotics. So generally, rehabilitation is an area where physiotherapy or other forms of therapy are provided to a patient in order to aid recovery, for example, from stroke. Generally, what happens is a human therapist, comes and gives guided exercises to the patient. And the idea is to help the patient form the neuronal connections again and recover from the uh, the stroke or any other kind of disability. Uh, since robots came, there was always an attempt to replace the therapists with the human therapists with the robotic therapists. And these are some of the examples here of some of the systems that have been tested extensively clinically. So you have the MIT Manas system. So here there's a 2 degree of freedom system, and the human subject has a visual cue given to him where he has to manipulate something on the screen, and the interface is this physical robot. This is a 2-link robot which has force control and an impedance control schemes implemented on it. And the goal is to say, for example, to overlap one sphere with another sphere or one circle with another circle. These kind of activities, gamified activities with hardware that can be tuned according to the requirements of the particular therapy. For example, this end effector position can be made very stiff, or it can be made very compliant, depending on at what stage of recovery this patient is. Again, this is another system. So for example, this is a Puma robot. This is a very early robot. So the Puma robot was also used for therapy and guided exercises. This one was developed by the Department of Veteran Affairs along with Stanford University. Similarly, there are other similar systems in which the general setup is there is a hardware which is interacting with the end effector. The end effector of the hardware is interacting, you can say, with the end effector of the human or the hand of the human. So there is a single point contact, and generally you have to achieve some task visible on the screen. So in recent forms, augmented reality and virtual reality setups are also being explored, in which instead of a screen, you have a head mounted device, which gives very immersive experience of performing these tasks. So all of these systems have an important component, which is the robotic component, which gives a physical interaction and which attempts to replace a human therapist. So the earlier systems were generally for the hand, the upper limb, but you also have other systems which are for gait. So there are some gait training robotic systems in which, for example, here this is the Locomat system, in which, along with the robotic system, which can provide different level of assistance to the human patient, there's also a mat underneath, which can be used to track the improvement in the gait. So in all of these robotic systems, one aspect that has been automated is the therapy, the delivery of the therapy to the patient. But another aspect that has been automated is also to collect the data that can be used to track the progress of the patient through the therapy. So all of these systems, these are generally bigger systems that are available in the hospitals. Some groups are also trying to explore smaller miniaturized systems that can be installed at the home of the patient, and it can be handled by the caregiver of the patient. Here I am showing, I did my postdoc at Vrije University, Brussels in Belgium, and there was a lot of activity going on medical robotics. So this is one of the activities that was going on in our lab. So you see here, this is my friend Kevin Langlois. He was a postdoctoral researcher there. He did his PhD from the same university and continued as a postdoc. So during his PhD, he developed this cuff. So the interface between the human hand and the robot is a cuff. There wasn't much research done on this in the literature, so he focused on the development of a sensorized cuff. Comfort was one of the criteria for developing this device. Then safety and data collection. So there are sensors mounted on this cuff that collect data and can tell us how the interaction between the robot and the cuff is taking place. So this is, you can say, is a pretty modern kind of system in which you have a robotic arm like this. So these kind of robotic arms are successors of industrial robot arms. So industrial robot arms are typically very high payload and very stiff robotic arms, whereas this is something called a collaborative robot arm, which have force control systems inside them. They have force and torque sensors, with which their compliance and stiffness can be changed programmatically. So that is what they have done here. So they are testing different kinds of compliance settings of this arm. Compliance setting simply means that while this robotic hand is trying to give some motion to the human arm, if you set a certain compliance, the human can resist that motion and can also push against the robot. These were not possible in earlier generation of robots. But with these new collaborative robots, these kind of applications are possible. So they are also exploring these kind of collaborative robots to directly make contact with human beings and provide therapy. So Kevin is working with you can see here he developed this system in our lab and then he took it to the hospital, and he is working with the clinicians in the hospitals, taking their feedback about what is desired in such a system, what is not desired, and also testing it on patients and making sure that these robotic systems match the clinical standards. So these kind of systems, you can say, are becoming state of the art now. And with these kind of collaborative robots, there is also a scope of extending it to various other kinds. For example, the same robot can provide therapy to the hand as well as to the leg. So these kind of setups are very useful. So this particular robot is a KUKA robot, KUKA IVA robot, which is a 7 degree of freedom robot for collaborative activities. So that was a brief about rehabilitation robots. Moving on, we have other areas which are the prosthetics. So it could be hand prosthetics. So here we see, I have shown some examples of the hand prosthetics. There are many commercially available prosthetics which are there in the market. For example, the iLimb hand or the bionic hand. The idea with this prosthetic hand is to replace a missing limb of the human. It seems very natural to extend the developments in the robots to these kind of fields, but this has its own unique challenges. One of the main challenge of such a system is acceptance by the user. So this is also something that I realized when I was doing my PhD. So I worked on multi-fingered robotic hands, but ultimately my thesis was on industrial application. But I also explored possibility of prosthetics, multi-fingered hands as prosthetics. But the key challenges here is less of research and more of product design kind of challenges. So acceptance by human users requires that the form factor should be similar to a human hand, and the aesthetic should be similar to the human hand. And apart from that, of course, there is functionality. For example, different kinds of grips should be possible. Here, key grip, precision grip, and power grip is shown. These are very common kinds of grips. So functionality surely is an issue, but aesthetics, form factor, weight of these arms are very important factor because if it is heavy, it will be simply rejected by the human user. So all of these make for a very good product design kind of problem. And the general approach that has been adopted by these commercial hands is to use very simple design. So here I am showing you some of the designs of these fingers. So for example, this is a crossed 4-bar mechanism. So this is a 1 degree of freedom mechanism. Although we can see that there are multiple fingers and there is possibility of 3 joints in each fingers. But these kind of fingers, they do not go for very high degree of actuation because actuators are heavy, they consume a lot of power. So the designs are made in such a way that few actuators are required, and thus the finger designs are similar to these. All of these are 1 degree of freedom fingers. For example, this is a cross 4-bar mechanism in which the proximal phalange and the distal phalange can move separately, but in a coupled manner. Here there is another finger, which is of the Michelangelo hand. Here they simplify it even further, and make the finger simple structure without having any relative motion between the different phalanges. This allows for these robotic hands to have a single motor per finger, right? We also have examples of other robotic hands in the literature. For example, the shadow hand is another hand, but the shadow hand has very high degree of freedom, and all the degrees of freedom are independently actuated. So apart from the hand, there's a big box that comes with it, which houses all the actuators. But that kind of scenario is not possible for prosthetic hands. So for prosthetic hand, generally low torque motors and compact motors are used, and one motor per finger is used. Apart from this, there are also various kind of sensing schemes which are used at the fingers. For example, force sensing resistors or other kinds of tactile sensors which are given in these fingers. So the idea is to make the actuation very simple and to allow the user to very easily control these hands. Having a very large number of degrees of freedom also creates difficulties in terms of controlling these hands by the user. The control becomes very non-intuitive. So these are some of the challenges in the design of prosthetic hands. There are a few companies that are working that I got to interact with when I was doing my PhD. So there's a foundation in Kolkata that is making prosthetic hands. Till now, they are making body-powered prosthetic hands, but they're also trying to transition to electrically actuated prosthetic hands. So body-powered prosthetic hand means that there is no motor or anything in the hand. There's a tendon which is there, and by pulling the tendon, the hand is actuated. But interestingly, even that kind of design gives a lot of assistance to amputees, and it has a good acceptance rate. On the right here, I'm showing a similar kind of thing for leg prosthetics. Same kind of issues arise for leg prosthetics. So you can see here the design of the prosthetic leg, and it has the various kinds of components, for example, the motors, the batteries, the electronics, everything in a compact structure. Again, the form factor is important, the aesthetics is important, but also the functionality. So this is a leg prosthetic, so the structural strength of this prosthetic is also very important. Apart from the physical structure and the controls, the interface is also an issue. The interface is also an issue here. So generally, EMG based or muscle activity based control is proposed for these kind of prosthetic hands. So earlier I was talking about a body powered prosthetic. So in body powered prosthetic, what happens? You have this robotic hand, and there is a tendon which is running across the body of the user to the other shoulder. And by flexing the shoulder, the hand is actuated. But that is body powered. If you have electrical motors on the hand, you should have an intuitive way to control it. So these kind of setups in which the attempt is to gather the muscle activity and to decode it and to send the actuation to the robotic hand. So there's a lot of work already in this. So signal processing, people are active in this field. So I had a when I was doing my PhD, I had a collaborator from electronic signal processing background who was working on this kind of problems. And then I was working for some time on the design of the prosthetic hand. These kind of collaborations are required in order to develop these kind of systems. These are essentially mechatronic systems. So mechatronic design is one aspect, but also the interface with the signals from the body is another aspect that has to be taken care of. Again, the group with which I was working, Vrij University, Brussels, the group is called Robotics, Brussels Robotics Group. They were working on leg prosthetics for a very long time, for around 10 years. And now the technology is very mature, and they are competing in events like this. So this is a visual from an event called Cyberthalon. So this is kind of an Olympic for people with disabilities, but they can use these kind of prosthetics and other augmentation. So here I have, he's my supervisor, Tom Verstraeten. He was my fellow postdoctoral colleague, Louis. So, and he is a patient who, a volunteer who has agreed to use the leg developed in our lab to participate in this event. So, of course, we did a lot of clinical study with this leg, but the aim of these kind of events is to test your systems against other systems and get some excitement from the funding agencies or people in general. So this was an event, Cyberthalon event, in which our lab had participated. So an interesting thing with the lab in which I was working was the level of implementation that they used to do. So we used to regularly have the patients coming in our lab and using our prosthetic devices and walking around in the lab. And these prosthetic devices also have a lot of sensors in which data is being collected, and the improvement and iterations of the designs are being done. So, but by seeing this, you can also see that there is a lot of scope for improvement, especially if you put such obstacles and different difficult tasks at hand. This prosthetic leg probably is useful for simple walking, but then these kind of events also help the researchers to test it in more extreme situations. So moving on, so there is another kind of technology also which are called orthosis. So for example, if the limb is not missing, but it is dysfunctional or it is weak in some manner, then these kind of active orthosis can be used. So for example, lower extremity powered exoskeletons that provide active assistance for walking. So with this, for example, at most of the places, this patient might be moving using wheelchair, but there could be other places in which these kind of exoskeletons can be used to assist the human subject to walk or to maneuver. Then there is the field of social robotics. Generally, these kind of activities are done in very few robotics lab across the world. But if they work closely with clinicians, and the goal here is to increase interaction of the patient with, say, a doll, which is a robotic doll. For example, if a child is suffering from autism, they can interact with the doll and can improve their behaviors and their emotional well-being. There could be other systems which are not human-like, but they also create some kind of excitement and play for the patients. There could be other systems like this. For example, this is a bandit system from University of Southern California. This kind of system is just guiding the human to do certain kind of exercises. So there is no physical interaction with the human, but there is social interaction with the human. So in these kind of interaction, the how the robot looks, what kind of expressions it is giving, what kind of motions it is giving, how acceptable are these kind of motions to the human user, these kind of factors become very important. Humanities, people working in the humanities field, social science field, also come into the group in these kind of research projects. And generally, they do user studies and what is the experience of the user after using these kind of platforms, and also to track the progress of the patients in different kinds of therapies with the help of such robots. This is another kind of system. Moving on, a major area in which robotics has been applied very successfully is surgical robotics. And this is also a field which a common public will tend to hear more of. So here, a Da Vinci telesurgical robotic system is shown. So it has the surgeon console, the console from which the surgeon is controlling the robotic surgical system. So this is the robotic surgical system in which there are multiple robotic arms with different kinds of surgical instruments. There is a motion controller, which is taking the instructions from the console and transmitting it to the surgical manipulator. The surgeon can look at the surgical area using the screen here, and there are certain manipulators which are there, teleoperation manipulators which are there, which he can control to give commands to these surgical instruments for example, cutting something or moving something. These kind of surgical robotic systems have been around, say, last at least 2 decades. They have shown promise and they have shown effectiveness in many kind of minimal invasive surgeries. So this Da Vinci system is very famous. This is available in many hospitals in India also. And also with many research groups, there is a research version of this Da Vinci telesurgical robot, which is available in many research groups across India. So many improvements on this can be done using those kind of trainer systems or research systems. So, for example, one of the improvements that is required is haptic feedback. So, when the surgeon is trying to probe something or is handling some human tissue, a haptic feedback means that the force interactions which are taking with the surgical instrument with the human tissue, the same kind of forces are also transmitted to the hands of the human surgeon using some motors installed in this teleoperation device. These kind of interfaces are still under progress, and a lot of work is going on in the research community. Then we have other kind of systems. For example, the surgical system that I showed earlier, the Da Vinci surgical system, this is a completely master and slave kind of device. So there is a teleoperation master and there is a teleoperated slave. But there are other kinds of system. For example, here you see there's a robotic system and there is an end effector of the robotic system. But this end effector is being controlled by a human hand of the surgeon. The goal here is not to do a master slave kind of system, but what you can call as a cooperative surgical action kind of system. So here, some of the so the hand-eye coordination of the human surgeon can be included here. as well as precise motion capability of the robotic hand can also be exploited. So it is kind of a system that takes the good factors from both the human and the robot and tries to make a system that can do very precise surgical tasks. So this system is from John Hopkins University. This is one of the universities in which there's a very strong collaboration of technical research groups, for example, robotics research groups with the hospital. So they have many such systems that they have developed. So apart from the overall system, the end effector, the part that is directly interacting with the tissues, is also an active area of research. The Da Vinci system, for example, uses a typical surgical instrument. So the normal surgical instrument is used here for teleoperation. But there are other systems, for example, the Columbia snake surgical system, in which a continuum robot kind of surgical system is used. This is another surgical system in which a 5 degree of freedom wrist is used. So a 5 degree of freedom allows many kind of orientations for the end effector. Then there are other systems in which there are bi-handed continuum robotic manipulator systems which are developed. So the main advantage of such systems is that they can enter any orifice in the human body, and they can be maneuvered remotely very dexterously. So they can reach various areas inside the human body and perform surgical tasks, for example, minimally invasive surgeries. Apart from this, I would also like to present some of the very, very recent works in the field of surgical robotics. So the systems of surgical robots that I showed earlier are all guided by humans, either through teleoperation or through active guidance of the end effector. But there is a lot of interest in the research community to completely automate surgical tasks. So there are particularly two areas of AI that are making this possible. First is the reinforcement learning, and the second is large language models and extensions of large language models. For example, the vision language models or the vision language action models. Vision language action models are extensions of large language models that are being applied to robotics. So here, such a system using reinforcement learning is shown. So you have the typical system in which you have a human operator and you have a surgical robot. However, there is also a system added to this, which you can say makes decision or controls the actions of this robot independently. So the first subsystem here is visual parsing, in which, for example, depth estimation and object segmentation is done. So if a particular set of tissues is being visualized by the camera, a depth estimation and segmentation of different parts of the tissues will be done. This will be passed on to a policy network or a perceptual regressor that outputs a state of the system, and then the state is passed on to a policy network that outputs the action. In the reinforcement learning framework, this policy will be trained in using reinforcement. This can be done in a simulator. So there are many simulators that can simulate motions of this robotic surgical systems and also the deformable tissues. So in these simulators, the policies can be trained, and then they can be used in the real systems. So reinforcement learning is an approach with which various kinds of you can say elemental tasks or small tasks, small skills during robotic surgeries can be automated. So a very generalized kind of policy. So by policy, I mean a controller. A very generalized kind of controller can be created. This could be a neural network based controller. This can be created by training the policy in simulation and by showing it thousands and millions of different kinds of surgical scenarios so that it is able to generalize to any new kind of surgical scenario. Similar activity is being done in what is called as I said earlier, the vision, language, action kind of framework, in which you have the image observations. And using the image observations, you generate a high level language policy. These language policies can also be intervened by a human by giving additional language commands. And then these language commands are converted into low-level language condition policies, and these policies are converted into robot actions. So this is a new kind of activities which are leveraging LLMs, language vision models, vision language action models, the transformer kind of architecture to develop or to generate robot actions directly from images from the endoscopes. So this framework of generating images, directly actions from the images and also conditioning on the language commands is a very interesting and very exciting direction of research, which is going to take off in near future. At the end, I would like to share some of my experiences about how this collaboration between the robotics groups and the medical groups took place at the various places that I have worked with. So my PhD is from IIT Kharagpur. So when I was there during my PhD, I saw a lot of collaboration between the mechanical department of IIT Kharagpur, which does a lot of robotics activities, and the School of Medical Science and Technology, which specializes in medical technologies. So we had people doing PhDs in our lab who had co-guides from mechanical department and School of Medical Science and Technology. These kind of collaborations were there. At Vrij University, Brussels, it had a sister hospital. So in the same group, they had another university, which was a medical college. So there was a very strong collaboration, which also evolved over time. So when I was there was already a strong collaboration between the mechanical engineering robotics group and the hospital. So we had started going to the hospital and testing our systems on the real patients. And again, I'm presently at IIT Jodhpur. So here also we have AIIMS Jodhpur as well. So there's a strong collaboration with AIIMS Jodhpur. There's a medtech program, and some of these activities have just started, but I'm very positive that these kind of robotics and medical technology kind of collaboration will only flourish further with the collaboration of IIT Jodhpur and AIIMS. So there's also a direct collaboration between Indian Institute of Technology and a hospital. So this is at few places this is being tried. So I would say that this is a unique kind of setup. So we also have a medtech program in which students exclusively get exposure to these kind of collaborative setups. Apart from this, I would also like to highlight some of the activities that we have done at IIT Jodhpur. We recently had a very prominent conference at IIT Jodhpur, which is Advances in Robotics, recently, just last month. So this is the main conference of the robotics community in India. So the robotics community in India is called the Robotics Society, and this is the flagship conference of the Robotics Society. We had a dedicated medical robotics full day workshop on medical robotics at the conference, and it was received very well by the robotics community. So if you are interested in future kind of activities, so this Advances in Robotics will happen next in 2027 at IIT Gandhinagar. So you can just search Advances in Robotics IIT Gandhinagar. You will soon find the next workshop, medical robotics workshop, that will take place there. Again, I want to point to some important publications, particularly to two very influential publications. One is the Springer Handbook of Robotics. So Springer Handbook of Robotics is kind of the, a very comprehensive book on robotics. If you are interested in gaining the first line of knowledge on any topic in robotics, your go-to reference should be Springer Handbook of Robotics. So it has more than 70 chapters on covering different aspects of robotics. It has every aspects of robotics covered in this book. So if you are looking for anything, just search Springer Handbook of Robotics and download the PDF, and then you can there are different chapters, and then you can look to the relevant chapter. You'll get the overview of it, the main groups working on it, the main publications, and the different details of the technology as well. Another publication that I want to point to is Science Robotics. So some of these works, recent works on surgical robotics and AI integrated surgical robotics I showed, has been published in the July issue of Science Robotics. The Science Robotics also focuses a lot on surgical side of robotics, rehabilitation side of robotics. So if there is very influential work in this field, you will always find it in Science Robotics. So you can also refer to this. So with this, I would end my presentation, and I'll be happy to have any discussion if there are any discussions.
Any questions from the participants?
हाँ जी सर, नमस्कार सर।
हेलो।
हाँ सर, नाइस लेक्चर सर। एक सवाल था मेरा कि सर आप तो बना रहे हो रोबोट्स के लिए, तो सर ऐसा रोबोट्स बनाया जा सकता है क्या कि वो इंसान को टच करके या कुछ भी करके नस पकड़ के, मतलब जैसे कि ब्लड शुगर होते हैं, हमें ब्लड निकालना पड़ता है तब जाके पता लगता है, राइट? वो रोबोट ऐसे हो कि हमें हाथ में पकड़ लिया और बता दे कि आपका ब्लड शुगर कितना है, या इस बंदे का बीपी ब्लड प्रेशर बढ़ गया है या नॉर्मल है, ब्लड शुगर सही है, या डिजीज पैरामीटर्स क्या है, टच करके इन इन नॉन इन्वेसिव टेक्निक। इज इट फिजिबल टू मेक लाइक दैट रोबोट्स? और कैंसर है या नहीं किसी पेशेंट को, हमें इतने सारे स्कैन करना पड़ता है। इज इट फिजिबल टू मेक ए रोबोट दैट he can tell by touch or by any means, because robot, you know, that is the invention of the human only. तो ये feasible है AI टेक्नोलॉजी में सर, बताएंगे प्लीज?
So
Roshan, shall I answer?
yeah, maybe you can answer. Yes.
Yeah. Behra sir, actually, to be frank, actually, we work on robotics, but the thing is that the ongoing research, it does not give you access to directly penetrate the human body. The first thing, कोई भी रोबोट को ऐसे एक्सेस नहीं मिलता है, और इट रिक्वायर्ड लॉट ऑफ प्रॉपर कंट्रोल सिस्टम, जो मतलब प्रॉपर तरीके से रोबोट को ट्रेनिंग तो छोड़िए, प्रॉपर तरीके से वो जाए, कोऑर्डिनेशन coordination and control. These both things are like more important for this whatever you ask, because blood nikalna, it is like for nurse or doctor itself, it is like somewhat it was like tough. अगर हम लोग मोटा हाथ रहता है, जैसे मेरा मोटा हाथ है, ठीक है ना, आई हैव फेल्ट कि ह्यूमन से ही ब्लड निकालने में बहुत दिक्कत होती है, हाउ कैन द रोबोट कैन, it will take time, but I am sure that it will come, but it will take time.
Yes, sir, I said that non-invasive technique. मतलब
नॉन
आजकल जो
इन्वेसिव टेक्निक में रोबोट का क्या मतलब है सर? रोबोट चाहिए ही नहीं है.
Generally, these
no,
kind of activities are not done in the field of robotics, but I understand what you're saying.
yeah,
So maybe you can look up things like, so for example, you said about blood sugar.
yeah,
I just remember seeing something that from the retina, an image of the
yes,
retina or the
yeah, yeah,
eyes,
yeah,
you can
yeah,
deduce something. So you will
yeah,
surely find some groups working on these kind of topics, image
yeah,
processing and these kind of classification
yes,
kind of
sir, yes, sir,
topics. Yeah,
yes,
yeah,
sir.
But that
I
one is
mean,
something else, right? That is a
yeah.
no, no,
That
sir.
is
image
different.
processing. It is like entirely new topic. Retinomyopathy. Retinomyopathy. It is like something different. It is based on the white color formation. White color, the layer, some layer. I don't remember that one. That formation. Actually, based on the coverage, it will tell the diabetic stage. That one is something different. But here it is like it is something different.
In for cancer, you said about cancer.
Yeah,
So again, I don't have very first-hand knowledge about this. So, but for example, there is certainly some the doctors certainly try to feel something without making any cut. They also try to feel the tumor, I
yeah.
suppose. They try to feel the tumor and try to guess what it could be, right? So those kind of
Sir,
things might be possible through robots also, because robots have sensors and they can probe. So if there is a tumor
yeah.
which you can touch from outside, right, and then you can try to get some knowledge about that, right? That might be possible, but I have not read it up, or I have not been exposed to it. But this could be one direction.
सर मैं एक आइडिया बता रहा हूँ आपको सर। मैं तो मॉलिक्यूलर बायोलॉजी, फार्मेसी एंड केमिस्ट्री से हूँ, तो मैं बता रहा हूँ, आप थोड़ा बताइए, अगर टाइम है तो 2 मिनट लूंगा बस। कि सर देखिए कि जब कैंसर होता है तो कुछ प्रोटीन और जीन्स अप रेगुलेटेड, डाउन रेगुलेटेड होते हैं। अगर डायबिटीज भी होता है तो कुछ ना कुछ प्रोटीन, जीन्स, मार्कर्स रहते हैं जो अप रेगुलेटेड, डाउन रेगुलेटेड होते हैं। तो दे आर नथिंग बट द मार्कर्स। तो ये मार्कर अगर कोई रोबोट्स को हम डिजाइन कर दे, आजकल देखिएगा ऐसे ऐसे हैं कि मैं चुटकी मारूं तो पंखा बंद, चुटकी मारूं तो लाइट ऑन ऑफ हो रहा है। यू अंडरस्टैंड नो व्हाट आई एम सेइंग? दैट काइंड ऑफ सेंसर्स आर देयर। सो मैं बोल रहा हूँ कि ऐसे सिग्नल्स अगर हम रोबोट को, जो मार्कर्स के नॉलेज, जो चीज है, ऐसे सिग्नल अगर दिया जाए, टेक्नोलॉजी आर डेवलपिंग, इट्स नॉट हम नहीं कर रहे हैं तो दैट इज डिफरेंट, कोई ना कोई तो करता होगा या सोचता होगा। मैं जो फील किया आपका लेसन सुन के कि ऐसा भी किया जा सकता है, अगर ये एक्सपर्टीज आपका अंदर है, रोबोटिक्स में आप क्या चिप्स यूज कर रहे हो, क्या डाटा दे रहे हो, अगर हम रोबोट ऐसे डिजाइन करें तो इट मे बी, मैं अगर आपका फील्ड में होता तो सोच सकता है ऐसे, अगर ये सारा काम अगर करता तो इट्स
एक्चुअली
इट्स
बहरा जी
मैं
आपको,
अगर गलत सोचा तो अलग बात है।
नहीं नहीं नहीं, जो आप बोल रहे थे ना, इसका मैं एक बोल रहा हूँ। अभी ये रिसेंटली एक न्यूज में मैं देख रहा था। व्हाट हैपन, पीपल, सम डॉक्टर, ही वाज सिटिंग इन यूएस and he performed surgery at some part of China. It is possible now, but it is like it was like through robotics. But the entire controlling scenario, it is the control mechanism. It will be operated by the doctor only. They, so far there are no standalone method which has been implemented to do any surgery, anything. अगर आप
Okay, let
ब्लड
me
प्रेशर के बारे में बोल रहे हो तो वी ऑलरेडी हैव दैट वन, व्हाट वी
Okay,
कॉल
let me intervene.
मैग्नोमीटर.
I think we can discuss this later. I think Dr. Behra can communicate with Dr. Hota or Dr. Yuvnesh. I think we should carry on
Someone,
with our
थैंक
session.
यू सर, थैंक यू, थैंक यू,
Rakshi sir,
थैंक यू,
someone
सॉरी
else
सर।
raised.
Someone else? Okay, please.
Alka,
who-
Alka, son. Dr. Alka.
Alka.
Yes,
Yes, Dr. Alka.
you can unmute yourself.
Dr. Alka, you can unmute yourself and you can ask the question.
And another question, it is from Divya, Dr. Divya. Good morning, sir. My mic is not
Mic isn't
working. Is
working.
it possible to generate or regenerate human brain biosignal via any kind of stimulation strategy? Yes, yes, it is possible. So, Dr. Ota, if you wish to say something,
And the question doesn't, it's
no,
not very
generate or
relevant for.
regenerate a human brain biosignal via any kind of
Yes. Yeah, maybe you
stimulation.
can answer this because I have
Okay,
not
fine.
worked on this kind of topic.
Okay, it is possible. The method is called through current actually. Through minimal current. What generally people used to do for example, to regenerate nerve cells, people will, as a doctor will probe the electrode into the patient brain where it is been. So, for example, stroke or something where the signal is not properly penetrating. Over there, they will insert the probe and they will supply it with VCCS, voltage controlled constant power source, in order to to provide stimuli to the damaged area, so to in order to regenerate itself.
So
It is
let me
possible,
add
it
this.
is being done now.
Yeah. So let me add one thing with this. So whatever the questions are being asked, let me tell you something. Hundreds of hurdles of ethical guidelines should be passed for this thing, which is like impossible. And basically, uh, these kind of research has now covered. And basically, these are now these are these can be used for medical purposes maybe 50, 70 years after. Right now, it's
Beyond that.
basically it's basically military grade research, and basically you cannot have access to this thing. And
So,
government can government can covertly do these things without any hurdle, ethical guidelines or something. But if you want to implement this for the common people, you have to pass hundreds of ethical guidelines. So right now, I'm confident that I cannot see these things in my lifetime. Maybe maybe next to next generation they will see this in his like 60s or 70s years of age.
Yeah, so
So
generally
सर सोमेदीप सर
every
yeah,
सर सोमेदीप सर
yes,
अगर हम
yes.
देखेंगे लास्ट 10 ईयर में स्मार्टफोन में कितना चेंजेस आया
it
एफएम मर
doesn't
So
गया
mean, sir.
smartphone is
एफएम मर
not
गया सर
directly okay,
सर
but
एफएम मर गया
smartphone is
डीवीडी
not
राइटर
directly
मर गया
interacting with human body. But
नो नो सर
you see, but still the effect of UV brightness, UV ray coming from the mobile screen, and which is affecting our eyes and our bodies, that is being right now getting researched. And I'm sure of that. They have to plan all this UV exposure to human health. Maybe in 5 years they have to change all of the mobile phones. So
yes sir sure sir
it's not easy.
that energy will be that will be different form of energy UV that's lower wavelength to larger wavelength it may be shifted whatever may be but what I feel that if the robot will hug you if robot will hug you he'll in touch with us senses then I'm not saying that he's going to do anything but I'm saying that if he'll touch us by means so by the feeling of sense or signal he can
I
say
mean,
he can
yeah,
generate a data
rather let me tell you, rather instead of hugging somebody, maybe they
yeah
can have a better scanner, which by
yeah
which they can scan the body,
same. So,
and
yeah
in which
MRI.
yeah, MRI, maybe MRI you can install it in a robot and they can do the MRI very quickly and very efficiently. That can be done.
No, no,
But
no. That also it is a problem because MRI required magnets.
yeah, exactly. That's
And you can't
yeah
place it
yeah yeah
anywhere.
So basically, whatever the showing in, whatever the movies in Iron Man or something that is showing, that is not humanly possible right now in this technology. Maybe that's what I'm telling. We need
it will
100
take
years
time
of
so definitely it will take time
100 years
but
of research to take
1,000
it in the
years.
farther and farther level,
1,000
right?
years.
Yeah, exactly. That's why people are. That's why people are so enthusiastic about alien tech, because they know they cannot build these things right now. That's why people are looking for aliens. I mean, if aliens have this technology, okay, let me give the technology, and I'll implement it in right now. So I mean, it needs a huge amount of research, and people are now more nowadays more into destroying people rather than keeping people alive, right? So they are more into developing more dangerous ammunition rather. I mean, they are going to implement robots in war rather than in the medical field.
Yes,
So
true, true.
So, okay, being said that, I want to sincerely thank Dr. Hota for his illuminating and insightful lecture on medical robotics. I mean, your expertise and depth of knowledge in this subject provided a comprehensive understanding of the subject, and your engaging presentation made the session both enriching and inspiring. Thank you very much for giving the lecture. And I now ask Dr. Gaurav to present the memento to Dr. Hota. Please, Dr. Gaurav.
Yes, thank you. Thank you so much, sir. Uh, Rakshit sir, you for giving me opportunity to felicitate our invited speaker, Dr. Roshan sir. So I would like to request Dr. Roshan sir to kindly accept this e-memento as a token of honor and gratitude from both organizer, and we are very thankful to you that you have accepted our invitation and conducted such an interactive, wonderful and informative session, sir. Kindly accept, sir.
Thanks a lot. Thanks for inviting me and hosting me in this session. It was very nice to present my work and have the interactions. Thanks very much.
Thank you. Thank you so much, sir.
Okay, let's invite our next speaker, Dr. Yunesh K. So, Dr. Yunesh K is currently serving as an assistant professor in the Department of Applied Mechanics at Motilal Nehru National Institute of Technology, Allahabad, Prayagraj, since February 2023. He holds a B in Bachelor's of Engineering in Biomedical Engineering from Anna University and MTech from in Biomedical Engineering from NIT Rourkela. And he did his PhD from IIT BHU in 2020. Following his doctoral work, he served as a National Postdoctoral Fellow at IIT Madras, and he got a sitar Bairak Gandhian Young Technological Innovation Award in 2019 also. He was awarded Frugal Innovation Award, and he has authored now 44 publications, including 5 book chapters, 31 journal articles, and 8 conference papers, and holds 3 granted Indian patents with 1 patent pending. His current research interests span bioinstrumentation and design, bioelectronic devices for point of care applications, AI/ML in biomedical signal and image processing, cellular analysis using semiconductor devices, and biomaterials. So, being said that, I invite Dr. Ivnesh to deliver his lecture. So, Dr. Ivnesh, the stage is yours. Please proceed.
Thank you, sir. Screen is visible.
Yes, screen is visible. Put it in the slide mode.
Yes, yes. Fine.
Yes, fine. Fantastic.
Okay, fine. So thanks for that nice introduction. So let's move on to the topic. So, good morning, everyone. So today my topic of presentation will be recent advances in wholesale-based biosensor. Okay. So learning objectives. At the end of this session, the attendees will be able to define the biosensor, identify its key component, explain various types of biosensor, their working principle, describe the different transducer mechanism used in biosensor, and at the end we will discuss the real-time application in health sector. So contents, this is the possible contents which I kept. So introduction. So define biosensor. As per IUPAC, International Union of Pure and Applied Chemists, the biosensor is defined as an analytical device that uses specific biochemical reaction mediated by isolated enzyme, immune system, tissues, organelles, or whole cells to detect chemical component, usually by electrical, thermal, or optical. Basically, in simple term, it is like based on the reaction, whatever it is been happened, so corresponding signal we will be getting either by means of electrical, thermal, or optical. So schematic representation here, actually they are like three main component. Broadly we can say one is like bioreceptor, then transducer, and remaining it is like electronic interface. So bioreceptor, it can be enzyme, antibody, nucleic acid, or cell type, cell or tissue. Transducer, generally it converts one response to another response. Here when we talk about biosensor, it will convert a biological response to a measurable signal. And measurable signal, it will go as it will be like the quantity will be small in a small. So we will be using amplifiers, then we will convert it into an analog to digital, and all the DU to A, all the process analog to digital, digital to analog, and all the other process will be taken care out, and finally we will be having some quantitative result. So basically in biosensor we will be measuring an analyte via a receptor ligand binding or interaction. So origin, basically, in 1962, Professor Clark carried out first experiment. He wanted to detect oxygen. So what he did, he used platinum electrode and to detect it. So this was marked as an origin of biosensor. So it was like the platinum electrode has enzymes over it. So for example, glucose oxidase. So as soon as it interact with the concentration of glucose, the corresponding H2 hydrogen peroxide further it will divide and it will give us a hydrogen and oxygen concentration. Based on that concentration, we will be getting the respected concentration of the analyte. So here, what he concluded is that the higher the glucose concentration, the more oxygen is being consumed. So lower the glucose concentration, more hydrogen peroxide is present. This means that either increase in hydrogen peroxide or decrease in oxygen can be measured, indicate the glucose concentration. So classification of a biosensor based on bioreceptor, for example, these can be referred as bioelement, biological element that specifically interactive with target analyte, okay, which we want to monitor. So bioreceptor based can be divided into enzymatic, immunosensor, DNA or RNA based, cell based. So enzymatic, generally we tell it as generations, okay. But generally the basic concept is that it uses enzyme, and by means of catalyzed reaction, it will we will get an quantitative result. So for example, if we take a blood, So it will have different types of moieties. So for example, different types of analytic. So when we have a particular enzyme, for example, if we take glucose as an analyte, and we have used glucose oxidase as an enzyme, then it will match with it, and we will be getting a measurable output. So immunosensor, it is like it uses antibody or antigen for highly specific binding. For example, so here the antibody, the detector antibody having the analyte will be captured by antibody, and due to the capture, there will be change in measurable output. So based on that, we will be having the quantitative result. For example, if we take source will bind based on the protein whichever interact, and we will be getting a measurable output. For example, when we don't have the target analyte, our resistance will be less. When we have the target of analyte, the current the flow of current will be disturbed, and we will be having a change in the response. Immuno or DNA based, it is like it uses nucleic acid probes to detect complementary DNA or RNA sequence, for example, genetic test. So here on the transducer, we will be having and deprobe DNA immobilized. So when it get interacted with the target, so there will be a change in corresponding thing. Electric. So cell-based biosensor, they uses whole living cells on the sensor plane. For example, here cell-based biosensor, it is made up of it is like generally it consists of two electrode. We generally name it a coplanar electrode, where we'll be having one electrode and one counter electrode. So one reference or counter electrode, we can say. So the what happens generally the current will flow from working electrode to counter electrode. So the based on the presence of amount of in simple term, based on the occupation, the current which is flowed from one electrode and the between the electrode get disturbed. So we will be getting a change in impedance. Change in impedance, it is nothing but it is a combination of resistance and capacity. So ECIS, electric cell impedance sensing system, is a common or conventional method which is being used for this type of test. So based on sensor based on transaction method, it can be electrochemical, it can be optical, it can be acoustic wave. So electrochemical transducer, the electrode itself will act as an transductor element in the presence of analyte. So basically, here the electrochemical biosensor detect the signal as a change in voltage or current in real time by coupling the electrochemical sensitive layer, the recognition element. The electrochemical sensor built upon it can be either 2 electrode or 3 electrode. If it is 2 electrode, then we will be having working electrode and reference electrode. If it is 3 electrode, then we will be having working reference and counter. So amperometric, ampere means current. So here the main concept is like we are going to measure the current produced by redox reaction. Okay. So amperometric biosensor measure the current produced by redox reaction that occurs at the electrode surface when a constant potential is applied. The current is proportional to the concentration of analyte. So amperometric biosensors are commonly used for detecting gas such as oxygen and glucose. So potentiometric biosensor. Potential means voltage. So these are the keyword based on the naming has been kept. So potentiometric biosensor, the measurement is based on potential difference between the two electrode. One electrode is usually reference and the other one is working electrode. When the reaction with when it reacts with the analyte, the potential difference is it will react, and there will be a change in when there is a reaction within the sample. So there will be a change in voltage. So that potential difference is related to the analyte concentration. These biosensors are often used for pH or ion detection. For example, pH, if you take, for example, the presence, they will be like in acid, there will be more H plus. In base, there will be more OH. So based on these difference, there will be like we will be getting the change in potential difference. So conductometry, conductance. So conductance, it is a thing. So it is nothing but it measures change in conductance of the solution due to presence of analyte. The conductivity is typically measured between two electrodes in the solution. The change in conductivity is proportional to the concentration of analyte. These biosensors are used for detecting various ion molecules that affect the conductivity of the solution. So impedometric biosensor, impede. Impede is a keyword which is nothing but opposes the flow of current. So impedometric biosensor measures the impedance, that is nothing but opposites to the flow of an alternating current of an electrolyte interface. The impedance is influenced by the presence of analyte, which causes the change in electrical property of the interface. These biosensors are often used for detecting biomolecule like DNA, protein, or cells. So optical biosensor, so everybody knows. It is like we are going to detect the light. So any example? So traditionally we can take an UV visible, right? So optical biosensor are a device that uses light to detect the presence or a concentration of biological molecules or analyte. These biosensor are based on the principle of optics and typically involves the interaction of light with sensing element and analyte of interest. So plasmon, surface plasmon resonance biosensor. Actually, it can be correlated with yesterday's Dr. Rajan Hari sir's work. Or here it will be like on the glass slide. For example, here we need to consider. For example, here the surface plasmon will be generated based on the change in when we, for example, we have gold nanoparticle. So when we excite with when we see the UV absorbance, so we will be having some spectrum, some absorbance peak will be there. So if we excite excite the nanoparticle using that particular particular nanometer, it will absorb the energy. Once it get absorbed, when the nanoparticle absorbs the energy, the electrons which is present in the valency beam will be shifted. It will move towards the conduction band. Due to this movement, it get excited. As soon as it attains the maximum energy, it will try to eliminate the charge which is being developed. Here when we here it is like in the terms of, here we will be getting surface plasma will be induced when we talk about gold or something. So SPR, here a thin metal film, for example gold or silver, will be coated on a glass surface. When the light is incident on the metal film at a particular angle, it excites the surface plasmon, which is nothing but oscillation of free electrons at the metal surface. The resonance angle is sensitive to the change in refractive index near the surface. Thus, those caused by binding of analyte at the sensing surface. By measuring the change in resonance angle, the presence or the concentration of analyte can be detected. For example, in this case, we have on the gold film we have used some antibodies. So antibodies. So when we flow antigens, when it get interacted, that is nothing but receptor ligand or antigen antibody reaction takes place. So what happen when it associate? There will be an increase. When it get dissociate, that means when it get dissociated. For example, once the analyte is flowed, what happen? We will change the analyte with some other, for example water or something. So what happens? It get washed away. So due to which a dissociation take place. So by this mechanism we can able to measure the number of analyte being present in that sample. So again, so fiber optic biosensor where the at the tip, it will be there will be like some antibody or something we can coat. So what happens generally? So the optic fiber will be used for both the transmitting and detecting the optical. So as it is being functionalized with some antibody or antigen, so they when it get interact with the analyte of interest, there will be change in due to the electrochemical reaction, there will be change in refractive index. By measuring that, we will get to know the concentration. So fluorescence based biosensor here, for example, the column will be having some fluorescence molecule. So when it get interact with some target analyte, there will be like change in fluorescence index. Either it will quench or it will enhance. Okay, based on that, we will be having the by correlating that fluorescent intensity or wave change, we can correlate and we can tell how much the concentration is there. So luminance based biosensor here, what happened? So here we will be using luminance material that emits light when excited by external light source. In the presence of analyte, either enhancement or quenching of luminance signal will take place, which can be measured to determine analyte concentration. Here, one LED will be used to excite, and the excited things will be detected by photodetector at the other side. So interferometric biosensor, here we will be having multiple cores. So each and every course we can have a different antigen and antibody coating. So what happen basically using an interferometric biosensor, we can sense different types of molecules in a time. So interferometric biosensor uses infrared pattern generated by light wave to detect change in infractive index near the sensor surface. Analyte bind causes a change in interference pattern which can be measured and correlated to the analyte of interest. Basically, the optical one, it is based on the shift in the refractance index. So colorimetric, we can tell it is like naked eye detection. Generally, what happens? For example, we have phenol red. Phenol red is sensitive to the the change in pH, or it is sensitive to OH and H plus ion. So what happens when we drop that phenol red to an for example, the one which is having the higher pH, they will be a color, they will be changing color. So simply by seeing that, we can tell the what pH by correlating with the standard chart. We can tell that how much what is the current pH of that solution. So scattered here, it is like it will be like based on interaction between light and the particle in the sample. So we will be so what happened? It basically the scattering based biosensor rely on interaction between light and the particles in the sample. When the light is incident on the sample, it can either it can be scattered in different direction depending upon the size, shape, and the refractive index of the particle in the sample. By measuring the scattered light, the information about the sample, including the presence of analyte, can be obtained. The scattered biosensor can be used in label-free detection of biomolecules, nanoparticle-based assays. So acoustic wave, the beauty is that here we will be sending an acoustic wave. So based on the interaction between the biomolecules on the surface, the acoustic wave, the spectrum, it gets changed. For example, we are sending 1 kilohertz of signal, acoustic wave. So based on the interaction at the sensing layer, the frequency of that, it will get changed. So based on that, so when we correlate it with we can correlate that with the concentration of analyte. So acoustic wave biosensor or type of biosensor that uses acoustic wave to detect and analyze biological molecules or cell. The type of the working principle of acoustic involve interaction of acoustic wave with the analyte, target analyte, which causes measurable change in the acoustic wave. So surface acoustic wave, again it is like we will be using your piezoelectric material, same phenomena. So based on the change in mass or stiffness of the surface, we can tell the binding affinity or binding affinity. So we can correlate that. So basically it is like, for example, we have a different pH. So based on the change in the acoustic wave, velocity and attenuation factor, we can tell that what is the pH. When it get increased, what we are getting, and how when it decrease, how we are getting. So bulk it is simple. So it will be having quasi crystal upon that thick quasi crystal. So what happen when antigen antibody reaction take place? The wave that travel towards the bulk material, it changes the acoustic property of the wave which is passing through that bulk material. It get changed due to the affinity or due to the binding of analyte. So by measuring that, we will tell. So we will correlate it with the concentration of the analyte. Generally, what happens? The mass get changed. So mass, it affects the frequency. So summary, so far we have seen various type of biosensor available, sensing of a variety of biomolecule. So now the question to the audience is that whether is it possible to use this biosensor for cellular analysis? The question is yes, but we need to do some modification. Why we need to do? Because commonly used technique to monitor cellular proliferation or viability include fluorescence spectroscopy, flow cytometer, and single endpoint assay such as MTT, WST assay, etc. And these traditional used method for monitoring cellular transformation mentioned above furnishes are either with quantitative or semi-quantitative data, apart from its requirement of a labor-intense protocol and expensive equipment needed. So moreover, these cell-based assays generally compromises the consistency and the reproducibility of the experiments. Hence, we used to have either 3 or 5 and replicas we used to tell, right? So in addition to these, we disturb the natural physiological state of the cells, resulting in their destruction. So therefore, to precisely monitor the cellular behavior to the external stimuli real time, non-invasive and label-free method is desirable. Typically, the biosensor can quickly detect various. We know that the biosensor can quickly detect various disease, thus dramatically reduces the heavy loads on regular clinical diagnosis in healthcare industry. Thus, that's why it can be widely explored in the field of pharmaceutical environment, food technology, and medical science. So typically, what does cell-based biosensor means? The whole cell-based biosensor. So cell-based biosensor, it directly uses the live cells. Hence, any biochemical effect of partial contact of live cell is converted into quantitative electrical signal by sensing layer. The signal comes to the transducer due to various phenomena of cells, such as a change in ion transportation, metabolic pathway, membrane potential, barrier resistance, and or maybe due to morphology, change in morphology of cells. So this is a schematic diagram where we will be housing the cell directly on the sensor, on the transducer. So by based on the stimuli applied, it will affect the characteristic behavior of these sensor, the transducer. So different types of cell-based biosensor. Traditionally, it is like a electric cell impedance sensing system. The principle of operation is based on the cells which are only the presence on the electrode affects the flow of. So, for example, if there is no cells, the current will easily pass from one electrode to another electrode, completing the circuit. If the presence of cells has been observed here, it will affect the flow of. Okay, it is basically so. Based on this principle, there are n number of different types of electrodes has been manufactured. The cost of these ECIS, it varies. The minimum it is like 27 lakhs, and it can go up to 48 or 50. And now we don't know because the tariff it is been getting increased day by day due to Trump's administration. So, and further, even though the instrument is costly, when we see about the sensor being used, for example, the distribution based on the type of sensors being used, the cost of the sensor per equipment per analysis will change. And to avoid contamination, we will be relying on a single time use. So these single time electrode uses gold. So usage of gold increases the cost, and further based on the type of experiment we want, the type of sensor, the various types of sensor, based on the complication of the sensor being developed, the cost will also be increased. So altogether, it is quite costly. So people tried to replace the use surface plasma resonance principle for cellular analysis. It relies on detection of refractive change in refractive index upon the coverage of the cell. So this was being introduced, but here it is like it is like maximum it will be focused to, and it won't be like all the cell, it won't provide us with what we need generally. So people on to the other methods like the quasi crystal where the based on the mass there will be the change in the attenuation of the exciting frequency. So this was then introduced. For example, when it is been addition, the mass will be increased. When it been released from that addition, when it get detached, again there will be change. When it get re-addes, then again it will get changed. So based on the mass, there will be a change in frequency. So what during my PhD, what I plan to do is like I wanted to develop a new whole cell-based biosensing device, which is like minimum in cost and easy to develop. So it was a theme, but so what I got inspired with the traditional detectors, where when there is no light, there won't be any current flow. Means the circuit is open. When the light falls based on the light proton, the current will flow in that detectors, and based on the flow, the based on the light proton being passed on the photo detector, the circuit get closed and the current will flow from one into another end. So this was the inspiration which I got. So based on this inspiration, I chosen metal oxide. So why metal oxide? When the surface of the metal oxide is being exposed to any particular environment, the variation in the electron charge transfer is being detected either in the form of change in resistance, capacitance, or impedance due to change in the metal oxide dielectric property, bulk electron mobility, grain boundary, bulk oximetry, etc. Further, so it is like now proven that based on when it get exposed, there is some changes being detected. Okay, what are the other advantage which I will be getting if I use metal oxide? The cost and the time, transparency and biocompatibility, etc. So fabrication of MSM, metal semiconductor metal based biosensor. Traditionally, we can have these structure everybody has seen probably. It is nothing but it is inspired by the capacitor or resistor, we can say, where we will be having two contact and one dielectric or insulator, something will be there. So this can be replaced by this method. So it is equivalent. So when we see the chip level circuit will have this like this phenomena, metal semiconductor metal. So for cellular analysis, I need to have some cup like arrangement so that I can drop the electrolyte over there, right? So this was the method. This was the update which this was the modification which I adopted. And what I did, I coated ZNO thin layer on that. These are the characterization results. The one which I fabricated, it matched with JCPDS number, file number 00891397 with respective peaks. And I got average roughness of 11.8 nanometer. And these are the FECM result. We can able to see the smooth and smooth without any voids. And spectra result confirm that whatever we got, it is like a ZNO. And silica, it is because of the bottom layer. I coated ZNO on the glass, so I got silica also. So UV visible by this method, we can able to see the absorption spectrum and energy where it get the energy band get. We can I calculated using UV spectra. So after that, I wish to know whether it retained the characteristic behavior of photo detector or not. So what I did, I exposed the developed MSM device to a darker area, then I exposed it with UV, because based on the observance we can able to see it is in UV range. So I exposed it with 365 nanometer laser, UV light for 15 minutes, and after that I measured the current. By applying voltage, I measure the current. I observe that there is an increase in current, which proves that the detect whatever the detector experiment I got inspired, it is been working. So after that, these are the fabrication steps which I utilize. After that, I immobilize gelatin on that surface in order to facilitate the cell adhesion property. So using FTAR,
इंटर्नशिप का
I
पैसा जाता है वहाँ पे
cross
हम कुछ
verified
नहीं है
whether
कि इसके बीच में
the
आपको
pumps
इंटर्नशिप भी अपने यहीं पे
which
कराएंगे
are necessary is been there or not. So after that, I did MTT to see the whether cell are live and metabolic active. Up to 96 hours I have seen. I have compared it with positive and negative control. I took positive as glass substrate and negative as the Zetano coated one, and I compared it with gelatin immobilized MSM device. So optical this is for 1000 cells I have shown. Here we can able to see up to 72 hours there is D. The number we can able to see. After that we can able to see there is reduce in the number. So it need to be reflect in our electrical characterization data. So here we can able to see if you look at the D, it is nothing but impedance plot frequency. And here we can able to the impedance got increased up to 72, or it means that the occupancy of cell on the top was there till 72 hours. After that it got detached. So as soon as the cell got detached or it got dead, I don't know, it might be apoptosis, or it may be due to detachment due to some other process like myotube formation or maturation of the cells, or etc. So as soon as the detachment happened, again we got a decrease in the impedance, which is linearly. It is it from the result it can be seen that as the day progresses, it linearly based on the increase in number, it will linearly increase. After that, it linearly decreased. So phase, it is nothing but phase gives us the morphological change. So when the cell attains its proper morphology, the capability of holding the charge will be high. So from the result, we can able to see when it was like a 72, a notable change in phase was observed in the lower frequencies, because when at the lower frequency the cell the flow of the VCC, voltage controlled constant power, constant current source with frequency, with respect to frequency, actually it passes the cell, it passes the outer the extracellular region of the cells. When we increase the frequency, it try to penetrate the cells, it try to penetrate this. So by this way we can able to see at lower the phase is quite higher, the quite is lower. It is because the capability got increased. So, and I wanted to see whether what happened when we increase the concentration. So I increased the concentration of myoblast cells to 3000 cells per well. Here we can able to see up to up to 144 hours. The concentration is quite increasing. After that, it got decreased. So it need to be reflect on to our electrical characterization result. So similarly, we can able to see in the magnitude of impedance plot up to some up to 144 hours it got increased. There were like increase in impedance strength was observed. After that, it was like we observed a recent decrease. And as here the concentration is quite high, there were no distinguish we could not able to observe the distinguish change in phase, but it is from the result we can able to see there is some change. So when we observe the Nyquist plot, we can able to see the charge, the semicircle, which is we can able to see the semicircles. So here it provides us a path to understand the availability of electron flow, the charge flow characteristics, right? So here we can able to see up to 144 hours, the charge availability was very less, but after that it got it got improved, so it started to move towards that lower regions. So summary, the result demonstrated that the dynamic behavior of myoblast cells is capable of altering the typical predefined characteristics of electrical behavior of the fabricated in vitro device. Further, the MSM structure is working significant to determine various cell function. For example, adhesion is possible, spreading, when it gets spread, we will be having the effect of phase change. Proliferation, it is nothing but multiplication of cells. So differentiation, when it differentiate, for example, the C2, C12, it may differentiated and to the mature level, myoblast to myocyte, right? So the maturation of cell, it is possible. The effect induced by cellular functional behavior is well correlated with both electrical and microscopic observation with a different concentration of cell density. Hence, MSM structure device can be used for various cell-based biosensing application. So further, now same structure I wish to use, but here I wish to use the cells which are like, so far it was like secondary cells. So here the proliferation is it is like more towards proliferation. I wish to see the cells which whose proliferation is limited, whereas the differentiation may be predominant, like some electrogenic cells I wanted to use. So what happened? So similar strategies I used, and I seeded I utilized TiO2 and SnO2 based devices, and I compared, because TiO2 generally titanium based implants has been generally be used. So I wanted to utilize that one. So I used the TiO2 and I compared it with SnO2 based method. Here I have seeded E18 neuronal cortical neuronal cells isolated from the mice. So from the infant mice. So here where we can able to see it is like here it is like the concept is like the numbers. For example, I have seeded 2 power of 2 into 10 to the power of 10 cells. For example, I have seeded 10,000 cells. So the cells which are active enough will only start outgrowth. Remaining cells will be there, but it will be like inactive form. So this was the concept. So here we can able to see as the days progress, the network formation got increased. We can able to see in the both. Here we can able to see broadly in the D, in the E. Here it is there. Here, but somewhat it is visible. So it need to be correlated. So here now what we need to get is that when we see when the days progresses, we need to have the impedance need to be decreased. So the you can able to see in the magnitude of impedance plot as the day progresses, the impedance of the device it get decreased. It shows that the due to outgrowth of neuronal cells, the due to its neuron the electrogenic behavior, the current is being the movement of current being the movement of current from one end to another end is being promoted. So phase due to the change. So here the same we can able to see the beauty of this result is that people uses TiO2 as a coating, but what we observed is that SnO2, even though it is similar, it has all the characteristics as like TiO2. But here the facilitation of the neuronal output was maximum in SnO2 than the TiO2. This was another beauty of this work we got. So in this work, we demonstrated the characteristic property of semiconducting nanomaterial based device get altered with the progression of functional behavior of neuronal cells as they dare perform various cellular function on the top of on the top. From the result, we relieve that a change in the characteristic electrical property of the fabricated device is well correlated with the functional behavior of the neuronal cells observed through microscopic and SEM image. Hence, we believe that these devices can be used for various cell-based biosensing application. So further, so far we have seen something like MSM based. So what happened? But here the current characteristics we can't get because the channel which we kept between one electrode and other electrode is 1 mm. So what we wanted is that we wanted something of something like diode. Over there, there won't be any channel. You see here there is no difference. But if we see here we kept 1 mm gap. So as here we have not kept yeah, there is no gap between the P and the N. So we believe that if anything happens on the top, it will affect the characteristic behavior, and we wanted to see how the current behavior current we are till now what happened whatever we have did is that we applied the voltage and we measured the current. So see, similarly, we wanted to see the characteristic behavior. So this modification I did. And cerebral cortical neuron from E18 processor that we used. So this was happening. And after that, it is on ZNO. So it is this same result from the same result we can able to see the network formation is very less in the day 3, whereas in day 5 it was quite high. So from optical, this was a ZNO coated on that glass substrate. Oh, that one was a ZNO coated on silica substrate. It was like opaque. This one we wanted to see the networks actually. Here we can able to see compared to day 1, day 3 has more. Compared to day 3, day 5 has more. So when we measure the current characteristic, the day image, we can able to see. This black one was device characteristics, and red one was when with media. So the current need to be increased with day it get progress, it is a thing. So what we got the same result. We can able to see from the IV result as the day progresses, due to coverage of due to outgrowth of neuron, due to coverage of neuronal outgrowth, axon and dendroids, the current which is being impaired by the secondary cell in previous cases, it been increased now. So here we can able to see the current characteristic got increased. So similarly the impedance, the magnitude of impedance, it got decreased as the day progressed. So summary, the present work demonstrate a change in electrical characteristic property of the fabricated device as a function of progression of cellular process exhibited by the neuronesis. So outcome revealed that the increase in the conductivity with notable decrease in the magnitude of impedance was found mainly due to the establishment of cell substrate interaction, as well as due to formation of synaptic junction between neuronal cells across the surface of underlying thin film substrate. So further, we also found that the characteristic electrical property were well correlated with the observed microscopic and semi image. So I would like to acknowledge all the funding agencies who facilitate this work. So special thank to Director MIT Allahabad, Head AMD, my supervisor, mentor, my scholars, Chancellor and VC, Calcutta University, Dean, School of Bioscience and School of Bioscience and Technology, Calcutta. Head Department of Biotechnology and Bioengineering. Thank you. I will be happy to have questions.
Okay, so any questions? The forum is now open for questions.
जी सर, नमस्कार सर।
हाँ नमस्कार।
हाँ सर, आपका वो 53 नंबर स्लाइड्स निकालेंगे प्लीज।
कौन से नंबर?
53
53
where you have done that MTT essay and
53 MTD,
near
yes.
about any slide of that MTT essay, sir. Please.
हाँ
Yes, sir. सर, मैं एक्चुअली एक चीज नहीं समझ सका। आप कुछ बायोसेंसर बना रहे हैं। यू सपोज टू प्रिपेयर सम बायोसेंसर एंड यू आर मेजरिंग द इलेक्ट्रिकल प्रॉपर्टीज।
yes,
एक्चुअली
changing.
what you are seeing in that, actually you did the MTT essay here. For what MTT essay you have done?
अच्छा MTD क्यों करते हैं बताइए?
आपने क्यों किया इसको यहाँ पे?
मैं वायबिलिटी देखना ना, सेल जिंदा है कि नहीं कैसे देख पाएंगे? फॉर
अच्छा, ये
एग्जांपल
कौन
इफ
सा
आई
सेल लाइन
गो
दिए थे
फॉर
सर?
अल्मर ब्रू और समथिंग, हाँ,
ओके
और
ओके
उस
सर।
वक्त क्या होगा उसमें, अल्मर ब्रू में क्या है ना कि आपका मिनिमम 10,000 सेल्स चाहिए, ठीक है
ओके
ना?
ओके सर।
वेरस मेरे पास मैं यूज कर रहा हूँ 1,000 और 3,000 सेल्स, उस वक्त
ओके
अल्मर
सर।
ब्रू काम नहीं करेगा, ठीक है ना?
ओके सर। ओके सर।
तो वेदर द सेल्स आर मेटाबॉलिक एक्टिव और नॉट ऑन द
ओके।
सरफेस, इसे देखने के लिए मैंने एमटीटी किया। इससे क्या पता चल रहा है ना, सेल मल्टीप्लाई हो रहा है, पॉलिफरेट हो रहा है ना,
अच्छा,
बस इतना ही था।
एक्चुअली ये सर यहाँ पे कौन सा सेल लाइन यूज किए थे सर आप?
सारे में C2C, ये सेकेंडरी सेल लाइन जो है C2C12 मायोब्लास्ट सेल्स।
मायोब्लास्ट सेल। एक्चुअली हम क्या करते हैं ना एमटीटी ऐसे में ना सर, नॉर्मली कोई भी फॉर्मुलेशन बनाते हैं तो उसमें टॉक्सिसिटी देख लेते हैं कि मेरा
हाँ
फॉर्मुलेशन टॉक्सिक
सिमिलर
है।
वे में, सिमिलर वे में
या
ही
या
फॉर एग्जांपल मैंने क्या किया, जेटोनो का लेयर लिया है, जेटोनो टॉक्सिसिटी भी बोलते हैं, एंटीबैक्टीरियल प्रॉपर्टी है, ये टॉक्सिक भी हो सकता है, समझ रहे ना? इसीलिए
हाँ
मैंने जेलेटिन इमोबिलाइज किया और चेक किया कि मेरा सेल्स प्रोलिफरेट हो रहा है कि नहीं।
सर, आप ये सेल किस में कल्चर किए थे सर? आपका ये
ये
आपका तो
एक्चुअली
ये
मैंने अपने जो डिवाइस बनाया था ना, डिवाइस में
हाँ
ही किया था मैंने। फॉर एग्जांपल मैंने उसमें इलेक्ट्रिकल कैरेक्टराइजेशन के लिए नहीं रखा, फॉर एग्जांपल मैंने ग्लास बनाया, ग्लास के ऊपर जेटोनो कोट किया, जेटोनो के ऊपर मैंने कप लगाया, उसके बाद उसे इमोबिलाइजेशन किया मैंने जेलाटिन से, उसके बाद उसमें सेल सील करके उसका एमटीटी किया।
अच्छा, तो आपका सरफेस में सेल अच्छे से अटैच हो रहा था सर?
हाँ
यस।
हाँ ये देखिए ना।
या या सर यहाँ पे जो आपने 120 आवर लिया है, मतलब नियर अबाउट 5 दिन। सर 5 दिन
हम्म।
तक सेल सर नहीं रहता है। बेसिकली हम तो कोई भी एक्सपेरिमेंट
नहीं
करते हैं
नहीं
दो
नहीं नहीं
तीन
नहीं
दिन
नहीं
तक
नहीं,
करते हैं।
एक्चुअली बात
आपने
ये है ना।
5 दिन क्यों किया?
नहीं नहीं,
हाँ।
1 मिनट 1 मिनट। 5 दिन तक सेल नहीं रहता है इफ
हाँ।
देर इज नो स्पेस टू ग्रो।
ओके।
अगर
यस
आप
सर।
कम सीड करोगे, यू हैव
ओके।
स्पेस आपके,
ओके।
मतलब देखिए ना, जैसे ऑक्यूपेंसी कम होते जा रहा है ना, सेल
हम्म।
डिटैच होने लगा। देखिए इसके बाद
या
ऑक्यूपेंसी
हाँ,
नियरली
दिख रहा
जीरो
है।
है,
हाँ, दिख रहा
उसके
है।
बाद डिटैच हो गया।
GRH में तो बहुत ही हो रहा है सर, कंटामिनेशन बहुत आ रहा है।
नहीं, कंटामिनेशन नहीं है, ये डिब्रीज है एक्चुअली, सेल डिटैच हो रहा है
अच्छा।
ना।
अच्छा। ओके।
और डिटैचमेंट की वजह से वो डिब्रीज लेफ्ट आउट हुआ है।
अच्छा सर, इसके इसके 5 दिन तक करके अपने, अच्छा 5 दिन तक आपका इसीलिए हुआ कि सेल काउंट कम था। आई
हाँ, कम
अंडरस्टैंड।
था।
इसके बाद
और
जो
और
एक्सपेरिमेंट
ऊपर
किया।
से एक्चुअली मैंने जेलाटिन डाला था, जेलाटिन मेरा फैसिलिटेट किया सेल
अच्छा सर।
अटैचमेंट को।
अच्छा ओके सर, यहाँ पे आप हमारा जैसे DMEM मीडिया सेल ग्रो करने के लिए FBS एंटीबायोटिक सारे चीज यूज किया था, या ऐसे ही नॉर्मल आप
नहीं
कैसे
नहीं,
ग्रो
सारे
किया?
चीज यूज करते हैं ना, ग्रो
सारे चीज
करने
ना,
के लिए
ओके सर।
न्यूट्रिशन तो चाहिए ना।
या
इसी
सर।
इसीलिए हम लोग जब करते हैं ना, फॉर एग्जांपल ये देखिए ना, इसमें
हम्म,
हम सेल के बिना भी एक बार ले लेते हैं, दिख रहा है आपको? सेल के बिना भी ले लेते हैं, उसके बाद सेल सीड
कौन सा है
करने के
सर?
बाद भी लेते हैं।
नहीं सर, कौन सा है सर ये? विच वन सर, दैट
नहीं
वन
नहीं नहीं, फॉर
ABC?
एग्जांपल आप सेंसर के कैरेक्टरिस्टिक्स अभी सेल के वजह से हो रहा है कि मीडिया के वजह से हो रहा है, ये भी हमें पता करना है ना। तो व्हाट
हाँ।
हैपन, पहले हम मीडिया का ले लेते हैं ऐसे बैकग्राउंड, मीडिया का
विच
ले
वन
लिया,
इज योर
उसके बाद
मीडिया
सेल
बैकग्राउंड
सीड
सर?
किया,
ए
उसके
बी
बाद
आउट
उसका एनालिसिस किया।
सर। सर विच वन इज योर मीडिया बैकग्राउंड सर? ABCDEF
नहीं नहीं
आउट
नहीं,
ऑफ द।
ए बी सी डी नहीं है ये, में आपको जो दिख रहा है ना, सभी में जो ब्लैक कलर का दिख रहा है ना, ब्लैक
हाँ
कलर
हाँ
का
हाँ
जो
हाँ
ग्राफ है, ये वाला
हाँ हाँ।
ग्राफ है। यहाँ पे लिखा
यस
है
सर।
ना मीडिया करके, कल्चर
कल्चर
मीडिया।
मीडिया।
हाँ।
हाँ।
उसके बाद
सर
सेल्स जैसे 24 आवर्स का रेड है, उसके बाद 48 आवर्स का ये ग्रीन है।
सर एक बात जानना चाह रहा हूँ सर, इलेक्ट्रिकल कैरेक्टराइजेशन मतलब आप क्या देख रहे हैं यहाँ पे? प्लीज, ये थोड़ा मेरा नॉलेज से बाहर है। आप थोड़ा सा अगर
अच्छा,
मुझे
एक चीज
समझा दें,
बताइए,
आई विल बी
एमटीटी में क्या
थैंकफुल।
देखेंगे आप?
सर
एमटीटी में
ऑक्सीडेशन
क्या देखते
रिडक्शन
हैं?
होता है, रिडक्शन होता है वहाँ पे, एमटीटी रिड्यूस हो जाता
नहीं
है
नहीं
तो
नहीं,
कलर चेंज
वायबिलिटी
देता है।
देखते हैं ना, सेल्स
या
कितना, अगर फॉर एग्जांपल प्रोलिफरेट हुआ है तो कितना कितना अमाउंट का हुआ है, वही देखते हैं ना।
ये सर ऑप्टिकल उसका, हाँ हाँ
सो
एब्जॉर्बेंस
सेम
ऑप्टिकल।
चीज हमने इलेक्ट्रिकल में देखा।
हाँ सर, ये क्या है, क्या करंट वोल्टेज, कैपेसिटेंस फ्रीक्वेंसी, मैग्नीट्यूड इंडिपेंडेंस फ्रीक्वेंसी, इंडिपेंडेंस, ये क्या है सर? मैं समझ नहीं सक रहा हूँ एक्चुअली क्या देख क्या रहे हैं, और इंस्ट्रूमेंट क्या है जो कि ये सारे इमेज दे रहा है, और इससे मुझे
एक्चुअली
क्या
ये देखिए,
मिलेगा?
ये है सेमीकंडक्टर पैरामीटर एनालाइजर, ठीक है ना।
ओके।
उसमें
हाँ।
एक्चुअली इंपीडेंस मतलब इट हैज बोथ रेसिस्टर कैपेसिटर,
ओके।
ठीक है।
हाँ।
तो अभी हमने क्या किया, हमने फ्रीक्वेंसी दिया, ठीक है, फ्रॉम 1K टू 100 Hz। और हम
हाँ।
देख रहे हैं कि उसका जो जैसे वो 1K से 1 MHz तक है, विथ वोल्टेज कंट्रोल्ड कांस्टेंट पावर सोर्स, ठीक है ना।
हम्म।
मतलब वोल्टेज कंट्रोल में रहेगा और पूरे में कांस्टेंट पावर देंगे, ठीक है ना।
हम्म।
इसके वजह से अभी क्या होगा, तो ऑक्यूपेंसी जैसे मास, सेलुलर मास इंक्रीज हो रहा है, तो वो क्या करता है ना, फ्लो ऑफ करंट, जैसे सॉल्ट वाटर इज गुड कंडक्टर ऑफ इलेक्ट्रिसिटी, है ना, ये तो
यस
हमें
सर।
पढ़ाया गया है। तो
या
सिमिलर वे में ये क्या हो रहा है ना, जो अगर सॉल्ट का कम कंसंट्रेशन होगा तो क्या होगा, करंट कम
करंट नहीं
फ्लो होगा ना।
या
सेम चीज हमने रिकॉर्ड किया, सॉल्ट के बदले में हमने सेल रखा बस।
अच्छा तो ओके। तो सर ये मतलब ऑलरेडी जब आपने कल्चर किया था, तभी बिगिनिंग से ही आपका सारे चीज का ऊपर ही सेल ग्रो कर रहा है और ये रीडिंग आपको दे रहा है?
यस।
ये, सर मैं अपना सैंपल भेज दूंगा, आप स्टडी कर देंगे सर?
अभी अभी थोड़ा दिन लगेगा, क्योंकि मैं अभी
नो नो।
अभी
नो नो,
प्रोक्योरमेंट
कभी भी सर।
प्रोसेस स्टार्ट किया हूँ।
सर कभी भी आपको जब भी टाइम मिले, मैं आपको सैंपल भेज दूंगा, अगर ये स्टडी कर देंगे तो दिस विल बी गुड वर्क
अब
कोलाबरेटिव
पर
सर।
सेल स्टडी कौन करेगा ये बताइए? मैं तो
सर
एनालिसिस तो कर लूंगा, कोई भी आ जाइए, whoever wants they can come to my lab, they can have the
आई
reading।
ये
पर
सर
सेल
ये
स्टडी एक्चुअली टेक्स क्वाइट टाइम एक्चुअली, वो उसमें हम लोग फैसिलिटेट नहीं कर पाएंगे फॉर डिटेक्शन पाथ, जो भी एनालिसिस है, मेजरमेंट जो भी चाहिए, वी कैन फैसिलिटेट। गेटिंग माई पॉइंट?
सर सर टाइम है ना, 1-2 मिनट लूंगा आपका, अगर दूसरा कोई क्वेश्चन नहीं है तो 1-2 मिनट लूंगा बस, 1-2 मिनट
चलिए।
सर। हाँ सर, मैं एक चीज जानना चाहता हूँ कि सेल तो अटैच है, जब सेल अटैच हो या डेथ हो जा रहा है तो उसका जो सॉल्ट है वो बाहर आ जा रहा है मीडिया में, तो
हम्म।
रीडिंग दे रहा है। अगर लाइव
नहीं
होगा
नहीं नहीं
तो
नहीं नहीं,
ज्यादा
देखिए
रीडिंग।
देखिए देखिए,
हाँ
एवरी टाइम जब भी हम मेजरमेंट लेते हैं ना,
हाँ सर।
बिफोर दैट आई यूज टू रिमूव द मीडिया विच आर कंटेनिंग।
ओके,
ठीक है ना?
मीडिया
तो
निकाल देते हैं आप।
मीडिया निकालकर उसे वॉश कर देता हूँ प्रॉपरली। तो जो भी अनवांटेड डिब्रीज है, फॉर एग्जांपल जो भी आप बोल रहे हो ना, वो
हम्म।
सब बाहर आ जाता है। ठीक है, जो भी
ओके
रहेगा इट
ओके।
विल बी लाइक नेग्लिजेंस, क्योंकि फॉर एग्जांपल आपका सेल है, सो
हाँ,
सेल इट इज नॉट इन, सेल इज डेड। डेड है तो
डेट।
मतलब फॉर एग्जांपल क्या है, उसके अंदर का जो भी पोटेशियम है इट केम आउट,
हाँ,
राइट?
सारे चीज, डेब्रिस ऑल्सो केम आउट, या
हाँ, सो एवरीथिंग केम
एवरीथिंग हैज
आउट,
बीन,
तो वॉट
इट
एवर
इज
इट इज
फ्लोटिंग।
देयर, इट इज नथिंग बट एक लेयर है
सुपर
which
नेटेड लेयर।
does not provide any effect on the flow of current। समझ
ओके
रहे हैं?
ओके। हाँ सर।
हाँ बस।
सर तो ये आपने सुपरनेटेड का लिया था या जो अटैच था उसका लिया था? क्योंकि मान लीजिए
नहीं
मैं
नहीं नहीं,
होल चीज।
अगर आप रिमूव कर, आप मीडिया चेंज कर रहे हो तो इसका मतलब क्या है, सिर्फ अडेयर, जो भी सेल्स अडेयर हुए हैं सिर्फ
वो
उसका ले
रहेगा।
रहा हूँ।
अच्छा अच्छा, वो जो अटैच्ड है वो उसका रीडिंग दे रहा है ये।
हाँ, क्योंकि
अच्छा,
फ्लोटिंग डज नॉट शो दैट मच इम्पैक्ट एक्चुअली।
ठीक है सर, आपसे कांटेक्ट करेंगे थोड़ा जानकारी के लिए। थैंक यू सर।
Okay, so I think I don't think anybody is going to ask any questions. I can't see any raising hands. So let's uh, congratulate Dr. Vivnesh K
Excuse me,
for
sir.
this nice presentation. Okay, who is?
Can you share your mail ID because my topic is also same as you.
Okay, okay. If you want to ask
I need
question,
your
please
help.
go ahead.
यस 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 मैम, बी।
Okay. No, no, I just ask you. Can you share your mail ID?
यस, इट इज यूमनेश के एट MNIT।
Okay, thank you.
हाँ।
So may I ask Dr. Gaurav to felicitate Dr. Vivnesh with a memento? Dr. Gaurav.
Yes, yes, sir.
Okay.
So, dear Yunesh sir, please accept this e-memento as a token of gratitude and honor from the organizing committee member, and you are the convener of this FDP. So I am very fortunate to felicitate you with this e-memento. Kindly accept.
थैंक यू सर।
Okay, so moving on to the next talk. So next talk will be delivered by Dr. Nishant Kumar Singh. So Dr. Nishant Kumar Singh is currently an assistant professor in the Department of Biomedical Engineering at the NIT Raipur. He holds a graduate degree in biomedical engineering from UPTU Lucknow, followed by a MTech in biomedical engineering and a PhD in computational biomechanics from IIT BHU. Previously, Dr. Singh worked as a technical support engineer at Medicines Private Limited Varanasi, a franchisee of Larsen and Turbo Medical System India. He also served as an assistant professor at SGSITS Indore. His research contributions include numerous papers published in international journals, presentations at national and international conferences, and contributions to several book chapters. So with this introduction, I invite Dr. Nishant Singh to deliver his talk. Dr. Singh, the stage is yours.
Yeah, thank you for my introduction. Am I audible to all?
Yes, 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 you are audible.
Yeah, let me share my slides. Is it visible?
Yes, sir. Bhejbile.
Okay, so is it visible to all?
Yes, sir.
Yes,
Yeah.
sir. Please go ahead.
Thank you for confirming. So let me thank you to the organizers, Dr. Gaurav and Dr. Yunesh, for giving me this opportunity. So I will be delivering the lecture on biomechanical modeling and analysis. So meanwhile, I will be uh, hiding my video because I am connected to my mobile. Later on, I will switch on. Yeah, fine. So, we will be focusing on the modeling and analysis of biomechanical systems, analysis and modeling, which are being used extensively from past many years, like past 20, 30 decades, like in other application, but in recent decades or 15 years back, biomechanical modeling and analysis that has played a very important role into the biomechanical systems or in biomedical engineering. So we will be focusing on how modeling are done and how analysis are done. So there are several methods of analysis which are used into the biomechanical system. But in this presentation, we will be only focusing on the analysis which are done from the numerical methods such as finite element method. So this is the introduction part, why in biomechanics, what is biomechanics? Like it is the application of mechanical principles, like all the principles which you have studied in your first year of graduations or in 12 intermediate, like the mechanical principles which are used into the living organism. So when we are using the mechanical principles in living organisms, that makes the combined word, that is biomechanics. So why we are doing the modeling? There are several reasons beyond this mentioned part. There are several reasons why we are using the computational model. Like beyond the imagination, like if you are going for a biomechanical or computational model, it requires more resources than the experimental things. So in focusing on the um, modeling of human body or the systems which are being modeled, that are basically modeled due to several reasons. Like if you are going for experimental setup, it requires a lot many trials. So it rids of many trials which requires several costings. So that is the most prominent reasons why we are using the computational models. Like we are also assessing the mm, mechanical properties such as stress, strain, or fluid parameters that are in a very complex manner, which cannot be the results which cannot be acquired or obtained from the experimental data. And we can also realize or visualize the stresses which are occurring on the bodies or on the systems or on the continuum. And there are several reasons beyond that, like we can also do the specific modeling, which are also the demand in the current scenario. And we can also do the preclinical testing, which are also which gives a estimate figure like what will be the output of any system which will be realized, or which will be actually, just for example, when we are going for developing an implant and putting into the body. So simply, if you think like we can't directly put these type of systems into the body, that requires many preclinical tests, many prototypes, many animal model study, many clinical trials. So doing computational models, it gives a very one estimated results like this will be the possible outcome of the model. So these are the prominent reasons, and beyond this, there are several factors due to which we do the computational model. So focusing on the computational model, like there is three broad classification which can be done like for computational modeling, or three stages we can go when we are going for biomechanical modeling specifically. That is the generation or development of complex geometry, uh, selection of very complex materials, and putting the boundary condition that are also very complex if you will think about the physiological system. Just suppose one person is standing on his single leg. What are the forces which he feels on his hip joint, or what are the forces which he feels on the knee joint, or other locations? These are very complex loading conditions which are very difficult to actualize in the experimental model, due to which we do the computational modeling. So this is the brief overview, like where other methods, these computational methods are being used. Like beyond these four mentioned points, like there are many places where we can do the computational modeling. Like we are many people are doing research into cardiovascular flow dynamics study, neuro helmet impact simulations, structural FEF, that is finite element analysis of the joints, patient specific uh, modeling, or AI augmented models. These are the demand of current research. And when we go for the complexity of material, when we are going for modeling of the complex material, it requires a lot in the lot resources into the experimental setup, and that can be easily interpolated into the computational model. Like when we just suppose we are going to assign a material properties of bone, that is material properties of bone is very complex and very anisotropic, and it is very difficult. Just suppose you are going to take a synthetic bone model and you are going to apply a material properties, that is impossible. So we linearize the experimental model but in computational model we can do the complex uh, material assignment. So it captures the nonlinearity and isotropy. It represents, it can, computational model can represent the heterogeneity. It can also personalize, and patient specific model can also be done. As you know, all the properties which are varied from person to person. If you will talk about two persons, their bone mineral properties varies. That can also be simulated in these type of computational models. It can also improve the predictions of failure, and it can also show the exact deformation which is occurring at particular location. So it can also simulate the disease progression such as cancer and other terminal diseases. So these are the beauty of computational model, and validation can also be done before in vitro and in vivo analysis. Like there are various kind of in silico validation which are done and which are actually being used in a big industries or by big researchers extensively. And we can also optimize the surgical procedure which are currently being used, that can also be called as a conventional procedures. Like several you can see nowadays, minimally invasive surgeries are done. Now, minimally invasive surgeries are done, which also is a prominent cancer. Like being actualized. So, and when you go for the complex modeling, this is the
Sir?
Yes, Eunice.
Sir. What happened?
I don't know.
Might be.
Just contacting.
मेरी
हाँ,
तो रानी
okay.
तो तुम ना ठीक कोई बात नहीं लड्डू भैया बन जाएगा
Please bear with us. There is some connective issue. He will be back.
Nishan sir, you are co-host now, so you can share your screen, sir.
yeah,
Yes.
yeah, yes,
Yes.
yes, yes. Now it is visible.
Yes, sir. It is loading.
Hmm. एक minute. Now it is visible.
No, sir. Yes, sir. Now it is visible, sir. Yes, sir.
Okay. And am I audible?
Yes,
Yes,
sir.
sir, you are
Yes,
audible.
Okay. Yeah, yeah, yeah. So sorry for the interruption. Let me resume. So we are doing the computational modeling, like third part when we are simulating the complex loading condition. So if you can see this model, this is the one model which is simulated that simulates the different loading conditions. Just for example, if you are talking about the hip joint. So if you are going for some rigid body modeling, you have to simulate all the muscles which are acting at this location that are represented by the red line. So if you'll think about its experimental modeling, that is very, very difficult. So these are the features. These are the features of modeling into the biomechanical systems, which give the precise outcome and estimated results by which you can further go for the experimental analysis or some fabrication of some component or some and some other regions beyond this. So let us start with some modeling and analysis. So this is the state of art of biomechanical modeling or the modeling into the biomechanical system. So as you know, like if you are going for analyzing a complex model or any model which is of the human body that requires the initial that is known as geometry. So if you're talking about a simple geometry, just for example, in mechanical system, crankshaft and other system, that can be easily designed, that having the particular dimensions, defined dimensions that that are measurable and that can also be easily designed into the CAD software. But if you'll talk about any modeling systems or the development of models which are done for a biomechanical system, just for example, a bone. So if you think about a bone that having a very, very irregular and complex geometry, their dimensions cannot be extracted or measured. So in biomechanical modeling, we use the image acquisition systems or image processing algorithm to develop the 3D models from the 2D images of the that are obtained from the scanners such as CT scan machines, such as ultrasound or MRI scan. So I will be demonstrating how we are developing a CAD geometry or 3D model of any human being parts from CT scan images or MRI images. And further, if you are going for a biomechanical system, one geometry is required. So we are developing one geometry, and we are removing several errors, several things which we have to remove or which we have to linearize to process it into for the numerical simulation. Further, we are going for assembling, like just suppose we are putting one implant into the human body. So similarly, the doctors, what he do, he cuts the disease locations. He put the implants, either it may be the metal implants, it may be the stents, it may be any components which are being fabricated synthetically and are being used into the inside the body. So that surgically how doctors are simulating, we can also computationally we can simulate it, or we can assemble it, and we can do the numerical analysis, and we can visualize the outputs. So these are the one processing steps, like we are acquiring the images from CT scans. These are the formats which are standard formats. These are the DICOM formats for that are the formats for medical images, and we are processing into the several softwares. Like there are several softwares which are commercially available. You can also use your own image processing codes to segment the region of interest, and we can also do the optimization. There are several commercially available softwares like 3T Matic, open source software like Geomagic. We can also use. These are the list of extensions which are being used. And further, we can also assemble it like Creoparametric, AutoCAD. These are the standard softwares and very popular software, which I think you all people know. And we can do its numerical analysis. Like in this presentation, we are focusing on the only numerical method, that is finite element method. So in ANSYS, that is very popular software, COMSOL, Abacus, and beyond that, there are a number of finite element software which in which you can do the simulations. And overall all the softwares which we are using in background, we are using only the codes which are uh, being used into the numerical method like finite element method, or the for image processing, what methods what we are using, what are the codes with what we are using, same thing that are used by these softwares. So these are the image acquisition representation. Like if you are going to develop a heap model, just for example, we are going for development of heap model, or we are going to extract this location of heap, that requires the CT scan images. So CT scan images that are acquired from the CT scanner, that are in the form of CT slices, that having the typical thickness of 1 millimeter to 1.5 millimeter. It depends upon the CT scan resolutions. So this is the representation of CT numbers of different tissues. Like if you talk about the bone tissue, its CT number is ranges from 40 to 1000, and it depends. Like if you are talking about a very soft bone, it having a very low CT number. If you are talking about very compact bone, like bone shaft, humor bone, femur bone, this type of bone having the outer shells that are very hard. So if you'll talk about a very hard tissue, their CT numbers will be rising. And if you talk about a very soft tissue, just for example, breast or fat or some ligaments or some organs such as kidneys, their ranges are very low. So accordingly, we have to segment our region of interest. If you are going to extract some femur bone from the obtained CT scan data, you have to select the CT numbers appropriately. This is the simple representation. Like you can see, this is the 2D images of 2D images of CT scan. Similarly, this is the 2D scan images of the same location, that is for MRI scans. And in image processing algorithm, first of all, we are going to segment the region of interest. So in this presentation, I am just showing how region of interest for bone are selected. So already I told you, like bone CT numbers are very high, or their Hounsfield field unit are very high. So this is the reason what we are selecting, like that is known as thresholding. And second step, you are doing the uh, segmentation, and then you are developing the 3D model. That three steps are compulsory followed into the software also. Either you are making your custom codes into several available software like MATLAB and others. So this is the selection of Hounsfield unit for the bone. The moment when we are selecting the Hounsfield unit, you can see it is changing the color. So CT scan images having all the information inside, like it having the some biological property, like it is differentiated from all the CT numbers. So its contrast is high. It is being selected. That is a very rough selection, which we have to manually optimize it. So in this, if I am going to segment this tibial bone, this is the range which we have selected, that is from here to here. And accordingly, we are doing the manual segmentation. That is the approximate selection, which is done by the thresholding method. Now we are going for the manual segmentation. Some automatic, semi-automatic algorithm are also used. That is one algorithm which was shown in this, that is region growing method. So by region growing, like if the pixels which is attached with any component, that will be automatically selected. So in this case, if I'm going to segment this location and we want to remove all these locations, so you have to detach all the pixels which is associated with this um, pelvic bone with this artery of the structure. So later on, we are going for 3D modeling, or the region which we have selected into the 2D spaces that we are going to merge with each other, and the 3D model representation will come on. So this is the representation of the 3D model. Like this is in background, like there are several algorithms which are used. So this mimics which I am using in this marching cube algorithm are used to develop the 3D model, and many smoothing factors codes are also used to smooth this model. So this is the actual extracted 3 model. That is, you can see this is very rough representation which cannot be used for numerical simulation. So at this point of time, if any experimental model are used at this, or if you want to do some research work on this 3D model, from at this point, this model can be printed or additively manufactured. And later on, if you are going for computational modeling, further it needs to be optimized. So you can see this is not the this is the triangle representation of the surface. If you will cut from here, you will see it is the hollow inside. This is the STL representation or the triangulation of the region of interest. That's it. So Uh, further, you have to optimize the model. Optimization requires several components which are carefully assessed, like smoothing. You have to check it, or you have to check the remeshing parameters. You have to see whether any holes is present that you have to remove. You have to fix all the triangles. Just for example, you can see this is represented by very small triangle. So this should be carefully uniformed, carefully all the bad edges of the triangles we have to remove it, or you have to fix the overlappings or manifoldings. So this is the one representation of optimization and modification into the model. Like actual model, this is the actual model of one pelvic bone, like which is extracted just after the 3D model generation, just after using the mm, image processing algorithm. Like in this, you can see these triangle representation that are very irregular, which needs to be further optimized. Like we are doing the uniform remeshing of the surfaces or uniform triangulation of the surface. This is the you can see from here it is more smoother than this surface. Like local smoothing, like these are the very sharp edges which cannot be processed into, or when you are going to process into the numerical simulation like FEA, it will give some error. So carefully you have to smooth this model. So this type of modification like doesn't impact on your output. Like carefully, if you are doing all this modification, it will never impact. It depends upon the sensitivity or the output what you want. So this is the filling holes, like this in this model, some holes were present which we have carefully removed. So this is the complete step of the optimization. And later on, we are removing the overlapping triangles. So this is the triangulated representation of this model. So I have shown into a very close view, like these are the intersecting triangles which are intersecting with each other. So these type of model cannot be processed, or the triangles which are some overlapping which is other, that you have to remove it. Some triangles are inverted. If single triangles will be inverted into one leg of triangle, it will the model will never be processed. So manifolding, like entrapment of some other body, unknown body, which you do not desire, that is entrapped into one body which you desire, that is also analyzed and removed. So these are the optimization method. And later on, this is the STL representation. So for finite element simulation, you require the model to be converted into the solid model. So there are several modeling methods which we are using to, that is one method, that is your curve modeling. In curve modeling, we are fitting the curves on these triangulated surfaces. And from the closed curve, we are making these surfaces as one these triangulated body as one surface. So there are several methods or several algorithms which are used, like we are using the T-splines or patches or non-uniform rational B-splines method. And later on, this is the representation of one triangulated surface which is patched throughout. So there, if you will talk about a triangulation surface of this model, you may find more than 1 lakh or 2 lakh of triangles. So that is estimated with the small patches. If you will talk about this patches count of the surface, that is very low in comparison of the triangulated surface. So these triangulation, when it is done, it is automatically converted into the solid model. So this is the representation, like this was the surface model or STL model which are optimized, and again it is converted into the solid model. Like it is in STL model, it was hollow inside. If you will talk about the solid model, it will be solid, like it having the volume inside. So this model is only appropriate for finite element modeling. So I will demonstrate one or two cases which are simulated or in our lab. So like we are taking one case of total hip replacement surgery. So total hip replacement surgery, when the hip is damaged of any for many reasons, like due to trauma or osteoarthritis, or there are several reasons beyond. So when it is damaged, like it needs to be treated. So earlier treatment is that medicine, some conventional treatments which are used. That end last treatment, that is the replacement of diseased hip with some artificial components. So this is the hip joint which is being replaced by several components. Like this is your hip stem which is fixed into the femur bone. This is the acetabular cuff which is fixed into the acetabulum, and some screw are used to appropriately position it at the particular location. So this is the components which are being used. Now we want to assemble it in a computational developed model of the hip, and if we want to see the outcome, what will be the prospective outcome of these type of implants. So you have to design the cup and all the hip stem components. Like you have to acquire the CT scan imaging, like you have to properly surgically stimulate the uh, uh, developed implant component into the developed pelvic, similarly as doctors do. Like if you'll talk about the inclination angle of the cup, that is usually fitted on 45 degree plus minus 3 degree, that is admissible. That depends upon the anatomical variability of the person. Interversion angle, that is 50 to 20 degree, or and inferior cup, that is also position at a line which is known as teardrop line. So this is properly a positioning which is done by the doctor. Similarly, we are positioning this into the computational model, and we are finally getting a replaced hip, and now we are going to analyze it. So we are making the screws which are properly positioned into the cup and properly fixed into the hip implant. So this is the one computational final model for analysis, which and like that having the implant components, the screws, and the bones. Okay, so like now we will focus upon the computational modeling. Like in this, we are focusing only the finite element method. There are other several methods which are being used by other researchers. So in what is finite element method? That finite element method is a computational, computer-aided mathematical technique for obtaining approximate numerical solution to the equations of calculus that predict the response of physical systems subjected to external influences. So this is one layout like how finite element method works. Like this is the problem domain. Like this is the one plate which having some screw. So to save the computational requirement, we first check about its repeatability, like if the system having some symmetry. So there is very minimum chance of symmetry into the biomechanical system. Like in this case, like we can go for symmetry. Like if you are going for half analysis, you can extrapolate to this analysis output to this system, but very limited variability will be, but still there will be a very limited variability because this bones dimension properties will surely alter with this. So there are minimum chances. That's why when we do the computational analysis into biomechanical system, it requires a lot computational resources. So efficient computational requirement is highly required when you are going to simulate some biomechanical problem. So this is the very simple representation, like is a problem domain. We are using a symmetrical analysis. So we are dividing the problem into quarter. We are discretizing it, that is known as meshing, and we are applying some material properties of which it is made up of, and we are applying the boundary conditions, and we are setting some set of governing equation and finite element equations, and we are seeing its output, mechanical output. So there are several resources which are used, like commercial software available, ANSYS, Abacus, Nastran, Patran, Mar, Edins, Ideas, and there are many open source finite element software which you can use it. So first of all, we are making the geometry, we are assigning the material properties, and we are assigning the boundary conditions, load constraints, and everything, and we are seeing the results. So if you are talking about the material property, like geometry, already we have discussed what we are using into the biomechanical systems that are being generated from the image processing algorithm from CT scan images. Like if we talk about the material properties into biomechanical system, that is a very complex type of materials which are being used. Depending upon the material complexity, surely your computational analysis will go into the non-linearity. But the moment when you are using a very complex materials, it will give more precise results. So if you are talking about a simple femur bone or any bone inside the body, it is very anisotropic, orthotropic type of property. But for the sake of simplicity, we always linearize it. So normally when you are going a very simple analysis, we can do the linear. We are putting the linear properties into the simulations, and we are doing some analysis. And just for as if you are going for very complex simulations such as spine analysis, so that having a very complex type of loading, that having a very uh, complex type of material properties. In that, we can also use, just for example, in intervertebral disc, that is having a very poroelastic type of nature, that is having a very fibrous nature, as well as there is having a very hyperelastic property that you want to actualize. So there are many methods which can be used, like poroelastic modeling, elastic plastic modeling, hyperelastic modeling. That all can be done. It depends upon your requirement, like what type of output you require and how much precise result you require. So that is the if you are going to simulate the same model which we have assembled, like we are using a very linear properties of these implant component, like implant component that are basically used metal component, as well as ultra high molecular polyethylene, that is made up of polymer material, that is also we are using. And we are using a very linear elastic property, and we are visualizing a very estimated result, what will be the estimated output. So boundary as for boundary condition is very complex in nature when you are talking about any systems, any joint, or any component or any organ. Just for example, you are going for simulation of cardiovascular systems. There that blood itself having very complex type of fluidic nature, fluidic properties that you want to simulate, that requires a very high amount of complex equations. It depends upon your requirement. So boundary condition, if you are talking about the structural analysis in this scenario, like if you are going for simulating this hip joint with pelvic bone, like there are a lot of muscle ligaments which are acting at this location, that require single forces which are acting upon, so that are uniquely evaluated from other researchers in the past, which we are their results which we are using in this computational analysis. So this is the boundary conditions, like you are using a very simple pressure or load, you are fixing the bottom boundaries. Like dynamic analysis can also be done if you are going for dynamical analysis, that you can do all the transient analysis, kinematic analysis, rigid body dynamic, fluidic analysis, anything you can do into the computational analysis. So this is the design and optimization. This is the one thesis. So I am demonstrating, that is design and optimization of triply periodic minimal surface based porous structure for bone application. So that is bone application means when large bone defects are there. Like large bone means this is the femur bone, that is normally known as the larger bone into the body. Uh, Tibial bone, that is also known as the large bone. Ulnar radius, these are the large bones of the body. When it having some defects means that having some tumor location, cancerous location, that needs to be terminated. If you are terminating it, like there is no other options to join it, so we are using a large size implants, that is known as segmentation of that is known as large bone segmental defect. So if you are going for, there are many traditional methods due to which this type of large segments are being treated. So in this, I am only demonstrating how we are making or optimizing the traditional implants to make it more efficient. So we are using some porous kind of materials, and porous uniquely porous type of materials, and there are many other biological requirements that are fulfilled from some porous materials. So earlier traditional methods what are used for treatment of this type of defects, that are uh, solid implants. So if you just suppose that defect is very large, just for example, it is round about 5 centimeter long defect, and you are going to place some 5 centimeter solid metal implant, just for example, stainless steel, titanium implant, that having a serious complications or serious issues, like serious issues, that first initial serious issue, that is it having the larger weight. So patient will feel the weight of the implant, and its functionality will be limited due to its weight. So if you introduce some porosity into that, or you make it the porous implant, that means you are removing some material, so obviously it will make the implant light. That is one advantage. Other biological requirements are there. If you are uniquely using the particular sizes of pores, that will be very beneficial to join the surrounding bone or the bone bonding. Just suppose this is the demonstration. Here we are putting this implant into bone with some anchorage system. So earlier, when patient will come on its functioning, or when physiological motions are being done. It requires some more fixation or more bonding. So these porous structures help out to give the more bonding mechanism. So these are the advantage of porous structure. So this is the demonstration how we are doing the mechanical computational mechanical analysis, or that is specifically structural analysis, and what are the fluidics which are used that are beneficial to promote this longevity of this implant. So this is the same factor what we have discussed. There are several joint diseases worldwide that having a very larger amount of burden worldwide as well as in India. So effectively, there is no sure shot treatment which are available into the commercial setting or in clinical setting. There is no sure shot implants or any implants which can cure a 100%, which can give 100% result. So all implants which are being being used into the clinical practices, some implants will having some drawbacks and some implants having some advantages. So continually researchers are implementing other technologies, and they are optimizing the implants. So this is the same discussion, which is what is segmental bone defect. This is the defect which can be occurred due to several causes like tumor, cancer, and other mm, regions. So this cannot be treated, or this is the cancerous location which are being removed, so it can never grow, bone can never grow. So you have to use some artificial implants over here to support this bone. So this is the treatment of bone defects. Like there are several methods which are being used. So in this simulation, we are autografts are also being used, allografts, xenografts, synthetic bone are also used. So we are focusing how it can be, and obviously metallic bone implants are also used. So we have incorporated some porosity into this metallic implants, and we have seen their outputs. So the type of porosity what we are using, like in universe, there are several type of porous structures which exist. Like if you'll talk about their cell topology, that is also open pores, closed pores. So normally, if you talk about the implementation of pores into the implant, that should be open pore, because it will allow the tissue or bone to ingrow, and it will improve the bonding and cell attachment with the implant. So if you will talk about the in this study, we have used a means naturally occurring triply periodic minimal surface based lattice structures. So these are several types are of porous structure which are being used. Like in this study, we have focused upon the TPMS lattice structures. So what are triply periodic structures? That are surface which minimizes the area locally or possesses mean curvature equal to 0, lying on each point of the surface with repeated geometries in 3 directions. So if you'll talk about the naturally occurring, like if you can see this is minimizing its surface. This is the soap films. Like you can this, if you are using this ring and you are uplifting the bubbles, like it will minimize the surface. Or if you can see this type of structures on butterfly wings, and there are other species also where you can see these type of structures. So we are implementing the porous structure, that is TPMS based on the implant, and we are seeing its mechanical and biological output. So these are the implicit equations which are used to develop these type of complex porous structure. Like if you'll talk about the primitive, if you'll talk about, these are the families of TPMS structures. Like in TPMS structure, there are many type of there is list of family tree. So like in this, if you are talking about primitive, diamond, gyroid, IWP, which is included in this presentation. So these having the unique trigonometric equation by which these equations are uniquely implemented into the MATLAB, and we develop some codes and we form this uh, surface representation. And the same thing what we are doing, we are converting this surface representation into the solid model, and we are assembling it with the implant, and implant is assembled into the bone, and we see the mechanical output. So there is C constant which are being used, like level set constant that is used, that give the precise porosity. Like if you will decrease, or that having range, like if you will talk about IWP, if you are increasing or decreasing the level set constant from -3 or beyond 3, it will detach all the pores. So, like if you require the connected pore, that range should be in this only, and that also gives the porosity of the structure. Like if you are varying the ranges from -3 to 3, it will give the unique porosity. So normally when we develop the orthopedic implants, like porosity that is defined, or that from the earlier studies, it is evident if you are taking the porosity from 60% to 80%, that is more beneficial for longevity of the implant. So this line is coming. Why? Am I audible?
Yes, sir. Yes, sir. You are audible.
Gaurav sir, this line came. I don't know how it is.
Sir,
So
some participant have used whiteboard.
okay, no issue.
Yes, sir. That's why it is coming.
Let's run like this only. So, so how much time I left, Gaurav sir?
Yes, sir. You can take, sir. You can share again your PPT. That's why it line will go.
Okay, let me share it again.
Yes.
Now it is fine.
Yes, sir. I am requesting all the participants, please behave like a teacher.
No issue. I think
Yes.
someone have done by mistake.
Yes. Yes.
Okay, so later on when we have the our unique type of uh, achieve porosity, like we are going for its bilayer surface generation, and we are capping it to make it a TPMS model. And later on, we are same thing we are doing. We are optimizing the model. We are removing the inverted triangles. We are smoothing the surface by uniform meshing. We are removing the over connected triangles. We are also removing many many disjoint bodies that cannot be processed. Like if you are using these bodies separately in one project, that will never process. So you have to remove it uniquely, and you have to uh, process it separately. So this is the one uh, layout, or the one algorithm which we have used. How that is very efficient. Like how to convert this STL unit cell of the TPMS model to the solid model. So we are after optimization, we are fitting the nerve patches upon the bilayer surfaces. Then we are checking its approximate fit with the STL model, like if it is uniquely matching with the original STL model, again we are processing with to for capping it the surface, and we are getting the final STL model. So same algorithm is done. Like if you are not achieving on any steps, again you have to repeat all the optimization technique and the generation of patches. So this is the unit cell. From unit cells, we have made lattices. This is the unit cell. by patterning into X, Y, Z direction, we are achieving the three-dimensional model. Now, this three-dimensional model you'll be uniquely analyzed. Like before applying on the computational model of the human bone or body, we are analyzing it. So first of all, we do some morphological analysis. Later on, we are doing the mechanical properties, and some fluidic analysis will also be demonstrated. Like it will show the complete picture how computational model prior to the implementation into the computational model of the body, how it is done. So morphological analysis of TPMS lattices. So that is what morphology we are assessing, like porosity, how it is, wall thickness. That is also a contributing factor for growth of the tissue or bone, cell proliferation. There are many biological parameters which are accounted into this morphological analysis. Like what will be the surface area after mapping of this porous structure on the body. That is also a very prominent factor. Like surface, if implant will have a larger surface area, that is more suitable for tissue attachment or tissue ingrowth properties. And pore sizes, what are the size of pore, that also plays the important role. Like earlier studies that have shown like from 100 angstrom, sorry, 100 microns to 600 microns. If there is pore sizes on the implant, that is more beneficial, and that will promote the bone implant bonding. So this is the pore sizes. This is all morphological analysis. How it was done, like the thickness measurement, and one ball is fitted into the bore to measure because the TPMS is very complex type of architecture. So these are the methods which are adapted to measure the pore sizes and thickness. So uniquely it was measured. Like again, porosity was measured by this formula. Like it is a very simple formula which you all know. And after analyzing the morphology of the lattices, lattices that are formed from the unit cells. So it was evident, like increasing the pore size, it will also increase the porosity. This is all four graphs which is drawn for primitive type of, varied type of, diamond type of, and IW type of TPMS structures. So it was evident, like if you are increasing the pore size, you are also increasing the porosity. But there should be a compromise between you cannot use a very larger, very high porosity or very high pore sizes, because from earlier studies, like 360, like it ranges. Somewhere reported from 100 angstrom to 600, 100 micrometer from 600 micrometer. Like if you talk about 300 to 600 micrometer, that is pore size which is beneficial for tissue ingrowth. So these all models come into these ranges. So if you'll talk about the primitive, that is more suitable in respect of garage diamond and IWP. This is one illustration. Surface volume ratio, like if you are increasing the thickness of the pore structures, you are decreasing its surface area. That is evident from this all plotted graph. And also, if you are getting the more surface area, that is surface area to volume ratio, when you are increasing it, you are getting the high number of porosity. So that is also evident from all the graphs. So if you talk about all graphs into this P, D, G, IWP, or all the structures efficiency, that cannot be assessed from single parameter. Cumulatively, when you are going to analyze the pore size, porosity, surface area, thickness, and plus mechanical parameters, then you can you have to make a compromise. What is your application point of view, and what amount of mechanical parameter you require, and what are the biological parameter which are accounted into. So this is the same thing. If you are increasing the thickness, like porosity will be increased. Sorry, it will be decreased. And if you are decreasing the thickness of the struts or wall, that porosity will be increased. That is vice versa. And next we are coming for the mechanical performance evaluation, like mechanical performance test of these lattices. So normally we are going to implement this porous structure into metal implant. Just suppose I am like, you can use any type of material intended for application, or the application where you want to use it. So in this presentation, I am only focusing on metal alloy. So like this is the medical grade titanium alloy, that is Ti6L4V. Its properties, we are taking it and we are applying into the on the lattices of porous structure, and we are giving some compression loads, and we are analyzing its mechanical performance. Later on, we will apply on the body. So this is the standard we have followed, like ISO 13314, to test it computationally. So same guidelines we have followed, like loading and boundary condition. A simple displacement loading, we have put like a very minimum displacement we have used to just deform, plastically deform it, and it will give the precise modulus of the model. So earlier, if you'll talk about the elastic modulus, that is round about 107 GPa. That is the solid titanium elastic modulus. And if you are making it porous, obviously its modulus will be also reduced. So what are the requirement of the medical implant? Like normally elastic modulus uh, of the synthetic material or the implant what you're using, that should be comparable or matchable with the surrounding bone. So normally surrounding bone property that ranges from 3 GPa to 30 GPa. So normally if you are reducing the implant elastic modulus, the phenomena which is happening for the solid model, that is stress shielding, that will be reduced. So stress shielding, that is normally weakening of the bone. For your understanding, just I am saying that is weakening of the bone due to the presence of implant. So if you are putting one implant into the body for 10 years, and that is giving the stress shielding phenomena, later on by that implant only that bone will break. So stress shielding phenomena, that is a very serious issue during this implantation, this implantation into the body. So that must be removed. So if you are using the pore structure, that is basically reducing the solid, um, part, and it is making it lightweight, and it is also reducing the elastic modulus. If it comes normally in the range of bone properties, that will give the excellent output, or the stress shielding phenomena will be reduced. So I have for 50 to 90% of porous structure was used, and it was analyzed. So we are using the ANSYS for simulating it. So all structures were uniquely simulated, like gyroid, IWP, primitive, all structures were uniquely simulated with the similar loading condition, what compression load and fixation what we have used into the same lattice size and same porosity. So this is the demonstration what we got. So from these mechanical analysis, we can see its output, like what is the compressive strength of this, what was the elastic modulus of this. If elastic modulus compressive strength, that is uniquely or approximately matching with the bone where we are going to apply this as an implant, that model is more suitable. And later on, we have to analyze its failure mechanism. Like obviously, you are matching its property that can also be achieved. Like if you require its mechanical properties that is in range of 20 GPa to 30 GPa, that is can be achieved by varying all the parameter, like level set constant parameter. You can vary its thickness, and you can achieve it any kind of way. But finally, if you are applying it and it is going to fail, so that type of material cannot be used, and that are not appropriate. So you have to make a compromise. And other thing, same computational model that can, if you are analyzing, that is more suitable, later on fabrication will also be done. So fabrication efficiency in current scenario, that can also, that must have to be analyzed. So if you are opting for metal manufacturing, that for SLM technique, just for opting like 0.2 millimeter, 0.2 millimeter, that is the minimum thickness by which it can be printed. So if you are opting this thickness below than 0.2 millimeter, it is of no use, because till below that thickness, it cannot be fabricated. So these are the challenges which you have to account when you are going to fabricate, or you are going to make a prototype of the material. So by analyzing, we have achieved all the porosity modulus that is listed over here. So it is effectively reduced. Normally, we have taken the elastic modulus that is around about 107 GPa, that is reduced in each and every porous structure up to 97% into diamond, 96% into gyrite, 97% into 90 IWP and 98.5. So it is all in approximate range that having more than 90% reduction. So maximum reduction that was happened into the primitive with the same compressive strength. So that this type of primitive, that is more useful of using this porous structure on the board. So, and later on, fluidic behavior analysis of this structure is also analyzed. Like we have made the mm, prepared the model for fluidic analysis, like primitive, like this is the fluid domain, and this is the primitive scaffold that is assembled together. This red color represents the fluidic part, and this is the implants which we are using. And a simple flow of fluid is used to assess the efficiency of pores and its fluidic flow. That will effectively mimic the flow of biological fluid into this pores if it will be used as an implant. So this is the model setup, that CFD analysis that was done into the Fluent, that is a module of ANSYS software, and we have seen several outputs. So porosity for 50, 60, 70, 80, 90% we have used for gyrite and primitive both. And 2 unit cells are used, because if you are using larger size of unit cell, it is fluidic analysis requires a high amount of computational uh, requirement. So to reduce the computational requirement, we have used only 2 unit cells that effectively given the output of the, so velocity vector contours, wall shear stresses, everything was analyzed. And this permeability efficiency, how much permeable it is for different for the fluidic flow. Like if you'll talk about the 50, 60, 70, 80, 90%, like these are the permeability which was assessed by these analysis. Wall shear distribution, that is wall shear stresses, that should be as low as possible. For any type of implant which is being used, because if you suppose in this implant some biological fluid is going to flow, so if wall shear stresses will be high, it will destroy the biological component or biological, just for example, some blood flow is going there. If wall shear stresses will be high, it will destroy the blood components. So Stress shielding is also analyzed, like it was implemented. This porous structures was implemented by this porous structure. One large implant which is being used for segmental defect that was developed, and this was resectioned like one virtual model of large bone defect was developed, and it was assembled into the model, and it was analyzed, and it was represented how stress shielding is being reduced from the bone models. Stress shielding is being reduced from by using the core structures. So same thing we have done, like we have used the CT scan data of the patient, we have done the image processing stuffs, and we have segmented our region of stress, that is your femur bone. And again, we have extracted from the whole of the locations, and marching cube algorithm was used, and femur model was developed. So, and effectively it was optimized by using the smoothing protocols, by using all the overlapping triangles, stuffs, and over connected triangles. All it was removed, and later on it was patched to get the solid model that is efficient for CAD modeling and finite element analysis. So this is the final model which we have achieved. This one large segmental bone defect was actualized by removing this component, and this component was mapped with the primitive type of PPMS structure, and we have achieved the implant, and it was again assembled or surgically assembled into the body, and same thing was analyzed with the physiological boundary conditions. So same representation it is here also, like we are using the bone resection, we are mapping the small unit cell, and we are making the lattice geometry, and we are intersecting with this defect, and we are getting this implant. So, and we are analyzing by putting all the physiological condition, a very simple physiological condition which we have demonstrated, but effectively it have shown like it is reducing the stress shielding phenomena. So how we have actualized, like stress shielding, that is the shielding of uh, stresses which on the bone. Like we have take two scenario. We have used one model for one model that is porous model, and one model that is solid model. That is the different view of both of the model, and we have applied the physiological conditions like material properties and isotropic properties we have used for the bone, and non-linear properties like additively manufactured titanium alloy properties we have used for this implant, and we have put all the boundary conditions. We have fixed the bottom, we have put all the greater muscle forces and the forces which are exerted on the head of the bone, and we have simulated it. So this is the force representation, a very normal force we have taken, and we have analyzed both the models. So this is the solid model, and this is the porous model. So if you will see closely, uh, the stresses which are transferred from the solid model, like if you'll talk about this is your solid model, that is the transparent view, and this is the bone which shows the contour of the stresses. So one Mises stress when we are plotting, that is 76.2, that is very low, which is the load are transferred very low in this bone. If you will talk about the at the same moment when we have simulated with the same scenario and boundary condition and same material properties, if you are using the porous type of implant, you can see the transfer of stresses are very high. So that means there is no shielding of stresses on the bone. So bone that also requires some mechanical stimulus to grow. So later on, over the implantation period, if you are using this implant, this porous implant, so stresses will be transferred that will promote the bone ingrowth. So there will be the reduction of stress shielding. This is the demonstration how we are effectively using the porous structure onto the implant. We are making it light, and we are reducing the stress shielding phenomena, and we are optimizing other phenomena like tissue ingrowth, cell ingrowth properties, cell transport properties, that is also optimized. So part 4, like we have developed a patient specific implant, that is we have taken a tumorized model from the hospital. We have collected from the ethical permission, like we have taken the CT scan data of one tumorized bone. We have resected the actual model and we have developed a unique implant that is novel, that we have that we are trying to uh, make it as a patent. So it is the implant which we have developed that uniquely translate the solid model into the porous model with same effective mechanical outputs. So this is the resections which are done into the mimics tools, like we have resected it, and uniquely that, like patient specific means that with the patient specific anatomy we have developed the implant model. So this is the demonstration of implant model which we have developed it. And why we have taken this component, that is having another concept, we are not going into inside that. So that is required for its insertion during the surgery. That's why we have taken two components and we have mapped same thing we have done into the mimic. This is the window which is being represented. So this is the shaft which will go inside the distal proximal femur of the femur bone, and this is the distal condyle in which large bore dia anchoring system we have used, and this is the locking mechanism which we have used over here. And now it is mapped with the porous structures to make it super light and uh, to promote the tissue bonding parameters and other to enhance the other properties. So this is the mapping, one demonstration of mapping of primitive lattices on the structures and finally making it a patient specific model. And later on this is all demonstration of the beauty of computational model, what we are using and how we can achieve the estimated result, and later on it can also be used for fabrication. And because right now there are restrictions for animal studies, uh, uh, like human trials, that are most difficult part. So these are the nearly impossible things uh, which can be achievably estimated from these computational models. So like validation, you can also do, like simply self validation can also be done in silico validation, like validation from earlier studies, or in vitro in vivo validation later on can be done, or animal study, clinical trial and fabrication, that all can be done. So if you'll talk about the first step of the ladder, that is your computational model. So that's all about this presentation. And softwares that are used for these type of simulations and modding, like materialized mimics, that is commercial, that is costly. Open source 3D slicer, that is easily available open source software. This is the unit of 3matic, that is the component of this software only, that is used for optimizing ANSYS or bench modules. There are many modules inside, you can use it. ANSYS space clamp used for CAD modeling. MATLAB software that is used for image processing algorithm, development of porous structure like TPMS structure. Creo parametric student version is also available, commercially also available, and research for research, that is also available. FreeCAD software and some Origin Pro and all that are used for a complete study. These are the short references, and thank you. So, am I audible?
Yes.
Yes, sir.
Thank you. Thank you, Dr. Nishant, for this beautiful talk. So I ask any participants if they have any questions. Oh, okay, so I guess
There is no question.
there is no questions. So I would like to thank Dr. Singh for this illuminating discussion, and I would like to ask Dr. Yuvnesh to felicitate Dr. Nishant with a memento.
Okay, fine. Give me a moment.
I have allowed the participant to unmute themselves. If they want to ask any query, any question from our speaker, they can unmute themselves.
No questions, it seems.
So people, yeah.
Sir,
Yes, sir.
sir, thanks for your time and support. Please
Thank you.
accept
Thank you. It's my honor to
the
have this.
e-memento as a token of our gratitude
Thank
on
you.
behalf
Thank you,
of
sir.
the organizing committee.
Thank you.
Please accept, sir.
Okay.
Thank you very much.
Okay.
Thanks a lot.
Okay. So as we come to the close of this enriching 5-day faculty development program, I would like to take a moment to express my sincere gratitude to all the eminent speakers for sharing their expertise and valuable insights, and to all the participants for their active involvement and enthusiastic participation throughout the session. Your collaborative contributions have truly made this FDP a meaningful and successful experience. With that, I would like to invite Dr. Gaurav to kindly take over and lead us through the validatory session.
Thank you, Rachit sir, for the invitation. So first, I would like to thank all the participants. Without your active participation, we cannot conduct this faculty development program with a great success. This is evident that we have crossed 300 participation who are continuously trying to join the meeting, and due to the limitation of our maximum capacity 300, they are not able to join. So the participant who are not able to join, they can watch the session on YouTube live. Okay, so now I would like to invite some participant if they want to provide their feedback on this FDP. So you can unmute yourself, and if you want to say a few words about the conduction methodology, the quality of the lecture delivered, the organization committee member behavior and all the thing. So this your valuable feedback will greatly enhance our capability, our ability to conduct the next FDP, and your feedback will be very important for us as a constructive way. We will take as a constructive way. You can do, you can provide your
You
feedback.
can express yourself.
Yes, you can express yourself as you want. So tomorrow, yesterday, we have received some faculty name who were interested to deliver the feedback session. So first of all, I am requesting Dr. Prem Shankar Gupta from the Tirthankar Mahavir University to deliver the feedback. Over to you.
Hello.
Prem sir.
Hello.
Yes, sir.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon, everyone, and respected seniors. It was a very very informative session, actually 5 days FDP, and it gives me immense pleasure to share my feedback on this faculty development program entitled Smart Health Innovation Integrating Imaging Sensors Biomaterials. Actually, I am from also from the biomaterials area. That's why the each session of FDP has a very high insightful covering advanced topic like AI in healthcare, smart biomaterials, imaging technologies, wearable sensors, and many more. The expert talk such as Nissan sir's talk was very informative. Actually, this was not my area, but today I have learned a lot of things, and these the all expert sessions was from the reputed institutions which offered valuable knowledge and sparked new research ideas among us, including me. My sincere thanks to the organizing team, including Gaurav sir, Sumedha ma'am, and Yunes sir, and all the speakers and coordinators for the conducting such a well-structured and enriching program. And finally, I am looking forward to more such as opportunities. Thank you, sir. Thank you, organizers.
Thank you, Prem sir, for your kind word. And now I would like to request, invite another faculty member, Muhammad Haider from the Swami Vivekanand Subharthi University, Meerut. Muhammad Haider, if you are here, you can unmute yourself.
Hello, Jai Hind to everyone. I am Mohammad Haider, Faculty of Pharmacy from Swami Vivekanand Subharthi University, Meerut. I'm highly appreciated
Sorry
this.
to disturb, sir. Sir, can you please switch on your video, sir? That's why we can take a picture. Yes.
Okay, sir. Actually, I'm at my home, so okay. Just a wait. Hello.
Yes, sir.
Jai Hind to everyone. I am Mohammad Haider from Faculty of Pharmacy from Swami Vivekanand Subharthi University. I really congratulate to you, sir, for organizing this kind of event and very informative. All the 5 days, all sessions are up to the mark and very nice. I heartily congratulate and thankful to you, the all organizing committee. Thanks.
Thank you so much, sir. Now I am inviting Dr. Sonia Rani ma'am from Geetam School of Pharmacy. Oh, ma'am, are you here?
Yes, sir. Sir, good afternoon, sir, and good afternoon to everyone. I am Dr. Sonia Rani, Assistant Professor, Geetam School of Pharmacy, Hyderabad. And so it's my honor to share feedback for this successful event. And it has been a great experience to attending this FDP. And first, I would like to express my heartfelt thanks to the organizers, Department of Biotechnology and Bioengineering, Galgotias Universities, and Department of Applied Mechanics, MNNIT Allahabad, for organizing such a meaningful and informative online FDP. So from the 6 days, we had learned a lot about a wide range of topics from the interdisciplinary research theme, such as AI involvement in biomedical application, bioprinting, and the medical imaging, medical robotics, micro needles as a recent techniques in a transdermal delivery approach, organ on chip health, and the many more topics covered by the experts. So the session, that session covered by the expert is from the top institutions and the research industries. They shared a very insightful and the current knowledge with us in the many topics. And as a like I'm a young researchers and the academician, so I learned a lot from this FDP. So from this FDP, I can explore furthermore, like ideas, new ideas to writing the research proposals and to collaborate to the researchers in my futures. So and I also want to thanks to the organizing committee providing the very nice platform to learn from the different departments at a single platform, from the biomedical science, computer science, and the pharmacy, and many more. So thank you very much for providing this single platform where I explore many things and learn many things. And I would like to congratulate to all the organizers uh, to success to this successful event. And I hope in a future you will organize such a insightful or meaningful that will be helpful in our research and as well as in my teaching. So thank you once again to everyone who made this FDP a successful, and wishing you all the best for your academic and the research journey. So thank you all.
Thank you so much, ma'am. Thank you for your kind word and motivational word. And next, I would like to invite Mohit Kumar from Tirthankar Mahavir University. Dr. Mohit, if you are here, you can unmute yourself.
Hello.
Yes.
Sir, actually, Dr. Mohit is under the evaluation, going for the copies evaluation. That's why I think he is not available.
Okay, sir. Okay. So next, I would like to invite Dr. Amreen Khan from AKTU. Are you here, ma'am? Okay, I think Amreen Khan ma'am is not here. So now the floor is open for the participant. Any participant?
Sir, I'm here.
Yes, okay, ma'am. Yes, ma'am.
My voice audible?
Yes, yes.
Is my voice audible?
Yes, ma'am.
Yes, ma'am. Please go ahead.
The organizing, first of all, I would like to thank the organizing committee. The FDP was really wonderful and it was very knowledgeable. And we got to know so many things through this FDP. And I'm waiting such more FDPs to be conducted. It's very, the FDP was very informative and each session was very well presented. Thank you, everyone.
Thank you, ma'am.
Okay, if anyone want to deliver their feedback, we can give you 5 minutes if you want to deliver the feedback by end
सर
of
नमस्कार सर.
Yes, sir. Yes, sir.
सर नमस्कार सर.
नमस्ते.
नमस्कार टू ऑल. सर मेरा नाम अशोक बेहरा है.
जी जी.
आई एम फ्रॉम DIT यूनिवर्सिटी देहरादून. आई एम वर्किंग एज एन एसोसिएट प्रोफेसर. माय स्पेशलाइजेशन इज मेडिसिनल केमिस्ट्री बेसिकली. तो मैंने इस सेमिनार से बहुत कुछ सीखा है. जैसे कि मैंने आपसे पहले बताया था कि सर थ्योरेटिकल अच्छा नहीं लगता है, तो सीखा. बट स्पेशलाइज्ड पर्सन्स आर देयर, गुड नॉलेज वर देयर, रिनाउंड इंस्टीट्यूट्स आर देयर. सो यहाँ पे मुझे इतने सारे हैं, तो सर बहुत बढ़िया लगा, बहुत सीखने के लिए मिला. जैसे कि मॉलिक्यूलर इमेजिंग प्रो लास्ट क्लास थे, सार एक थे, और दूसरे सार जो हमारा न्यूक्लियोटाइड्स पे काम किए, तो उनसे भी बहुत नॉलेज मिला मुझे कि प्रोजेक्ट डिजाइन किया जा सकता है. जिससे कि और पॉलीमर्स तो बहुत सारे हैं, बहुत सारे काम हुए हैं. तो बहुत अच्छा रहा सर एज ए होल. बट एक चीज मैं सजेस्ट करना चाहूंगा कि सर लेक्चर सारे बहुत हो जा रहे थे सर, तो ये नेक्स्ट टाइम थोड़ा सा सोचिएगा कि कंटिन्यूअसली हम 10 बजे से बैठते थे और 3 साढ़े 3 बजे उठते थे. देयर वाज नो गैप, तो इट वाज टू मच फॉर अस. तो ये अगर आप नेक्स्ट टाइम अगर प्लान करेंगे कि थोड़ा सा 2 क्लास, फर्स्ट हाफ सेकेंड हाफ 2 क्लास, दैट्स एनफ. तो फिर भले दिन ज्यादा हो जाए तो अच्छा रही. मेरा पर्सनल रिक्वेस्ट है बस,
Sir,
क्योंकि
thank
बहुत हो जा रहे थे.
feedback, sir.
या
Actually,
दिस पार्ट वाज द
I have organized approximately more than 20 FDP, sir, on online platform.
Yes, sir. Yes,
And
sir.
actually, the problem is that in the online, if you will discontinue, if you will have some lunch break, then participant, the faculty member are not usually join again. and it is very difficult for us to make them join. And actually that's why we have not given any gap, but we have given gap for the one day due to the because one of our speaker has closed their session before on their scheduled time, and one of the speaker has not joined on the earlier, not able to join earlier, so that's why we have given one lunch break for at that time. But usually we are not giving a lunch break, sir, because the participants are not rejoin, and that is the real time difficulty. Also, if we have also give in the previous FDP, we have conducted with the Ayush Ministry for the yoga in healthcare, and in that program we have conducted a great number of hands-on training and yoga session, but a participant not usually switch on their camera, they are not in the online platform, they are not interacting. That is the real time issue for the online FDP program.
नहीं सर,
But
जिसको
one
सीखना होगा तो
wonderful
सीखेगा
thing is
जरूर।
that we can accumulate, we can gather participants from the across India and the pan India if we are conducting the online platform FDP. That's why we have conducted, we have kept it in the online. Okay, sir.
ये सर, नो सर, ऑनलाइन बहुत बढ़िया है, क्योंकि सर कहीं जाना नहीं है, पैसा का खर्चा नहीं है, कुछ नहीं है, रजिस्ट्रेशन फीस है अभी तो ओके, बट जाने आना रहना दैट्स ए ठीक लगता है मुझे तो। नॉलेज लेना है तो कहीं पे भी बैठ के, अभी देखिए हम कितने सारे इंटरेक्शन कर रहे हैं IIT NIT पर्सन के साथ, और सीख भी रहे हैं नॉलेज। अब इंटरेक्शन भी हो रहा है और नॉलेज भी बढ़ रहा है, तो मैं सोचूं दिस इज वेरी इंपॉर्टेंट थिंग। एंड ये सजेशन था कि सर,
अशोक जी
हाँ सर,
बाकी अभी बहुत सारे चीजें हैं, तो आप अभी ठीक है ना, बहुत सारे मतलब टाइम लिमिट है, हम भी दूसरे ऑर्गेनाइजेशन से हाँ, तो बाकी अपन कॉल पे बात करते हैं, अभी आगे का प्रोसेस कंटिन्यू कर रहे हैं।
Sir, I am also requesting the participant to switch on their camera. That's why we can take a group photograph also. And if any participant, any faculty member, respected faculty member want to deliver their feedback, you are mostly welcome, and you can deliver your feedback, sir.
Dr. Gaurav, this is Professor Prabhat Srivastava from Electronics Department at Galgotias University. My heartfelt gratitude to the entire team. A great session every single day. So many, I mean, the contents were so in depth, thoroughly covered. No words to express my, gratitude for it. Every session was a great session. Many more such sessions and FDPs to follow in future. Thank you and best wishes.
Thank you so much, sir, for your kind word and blessings. Thank you, sir, for joining with us.
Dr. Neha, please go ahead.
Good afternoon, Gaurav sir, and everyone in the organizing team. So first of all, I would like to thank Dr. Gaurav for giving me an opportunity to attend this FDP. And I was really, I really enjoyed attending all the sessions. And what I would like to convey is that the choice of speakers was really very good. And the topics that were covered were really, it was a very wide range of topics covered, from biopolymers to biosensors and disease detection, which is, quite a much things that are needed in biomedical and bioscience field. And normally we don't get to attend topics, get to attend to speakers, listen to speakers on these different kinds of topics. So it was a very nice experience attending this FDP, and I hope we have more such sessions on biosensors, because it's something which is very much in demand these days. So thank you. Thanks a lot. Yeah.
Thank you. Thank you so much, ma'am.
Divya ma'am, please.
Yeah, good afternoon, everyone. I'm Divya from Bhilai. I'm from RSR Rumta College of Engineering. Actually, this FDP is very much important for me because I'm from soft computing era. You can understand very well. Biosensors are, just like a new thing to me. So basically, yeah, basically this FDP provides me the comprehensive knowledge about the emerging technologies regarding biosensors or wearable sensors, specifically relevant to next generation smart systems. So the hands-on components which the speakers discuss from regarding various environment and regarding various diagnostic domain, that is very insightful for me. So thank you so much to the organizers for providing us this platform so that we can gain so much knowledge. Thank you so much.
Thank you so much, ma'am. So can we conclude the session? Or anyone want to provide their feedback?
Express anything.
Anyone?
Fine. Fine, sir. We will conclude.
Okay. So let me conclude with a small report I have prepared for this FDP program. So good afternoon to all respected dignitaries, distinguished speakers and participants. And it is both an honor and privilege to me to present the event report on behalf of our organizing committee member for this 6-day faculty development program on smart health innovation, integrating imaging, biosensor, and biomaterial, jointly organized by the Department of Biotechnology and Bioengineering, Galgotia University, and the Department of Applied Mechanics, MNNIT, Allahabad, Prayagraj. I am greatly appreciate the effort of our friend Yugnesh Kasi Viswanathan for the wonderful coordination and acting as a catalyst behind this FDP. So this FDP was envisioned as an interdisciplinary platform to promote the academic exchange and innovation at the interface of biotechnology, imaging sensors, AI, and biomaterial, with the aim of translating this technology into the next generation healthcare solution. So we begin our journey on 12th July, 14th July with an inspiring inauguration session, and we have privileged to be jointly by the Professor R.S. Verma sir, our chief guest, Director MNIT Allahabad Prayagraj, who has accepted our invitation and graced this inaugural session and delivered address. And Professor, I am also would like to thank Professor K. Mallikarjuna Babu, Honorable Vice Chancellor of Galgotia University, along with senior academician including Professor R.S. Sharma sir, Professor Ajya Bharti sir, Professor Abhimanyu Kumar Jha sir, and Dr. Yugnesh K. This session set the tone for a higher impact, knowledge-rich program, and we are proud to share that overwhelming response we have received for this FDP. We have received more than 1,500 registration across India and abroad. So out of which 400 active participants attended the session via the Zoom and YouTube link. So the FDP featured 2 keynote speakers, 26 invited speakers that represent from the premier institution like IIT, NIT, IIIT, Central University, and industrial leader like GE Aerospace and Ericsson. The 6-day technical schedule that cover a wide spectrum of theme delivered by and through the leader and innovation. So day 1 covered foundation topics such as AI in healthcare, polymer biomaterial, thin film sensing, aerosol delivery optimization. Whether day 2 introduced the advanced application like micro needle, smart biomaterial, 3D bioprinting, and sensor driven IoT trust management. Day 3, we have in the day 3, the speaker featured some development in wearable inotropic sensors, musculoskeletal modeling, sign encryption for medical data, and molecular imaging technique. In the day 4, we have explored the cutting edge innovation like radiogenomics for brain cancer, quantum enhanced decision system, prompt engineering in AI, and osteoporosis diagnosis. In the day 5, we taken the insight into the Parkinson disease diagnosis, metamaterial based biosensor, thermodynamics modeling of nucleic acid, and biosensing. In the last day, that is day 6 today, our concluding day, it offer a futuristic view on biomaterial robotics, machine learning in medical imaging, and biomechanical modeling. So these topics were well curated, multidisciplinary, and forward-looking alignment with the FDP core objective of integrating innovation into healthcare system. So, and all effort goes to our friend Yuvnesh. So the FDP provided to be a platform for the knowledge enhancement across academia and research. It can also offer a collaborative exploration because several of our keynote speaker and invited speaker invited the participant to do collaborate, to write a mail, and they have provided a platform for the intersection between the engineering and biological science. And this FDP also evident for the promotion of AI-driven biomedical innovation for the real-world application. The participant also responded positively, and I am fortunate to have a participant like you who have make this FDP a great success with a resounding success. And you have asked several query with our, you have interacted with our invited speaker and keynote speaker. So as we are concluding this remarkable week, I extend my heartfelt thank to all the keynote speaker and invited speaker for sharing their valuable time and insight. Our organizing committee member, our session coordinator from the Galgotia University and from the MNIT Allahabad for their seamless coordination. And I am also thankful, greatly thankful to each of the participants whose presence and enthusiasm make this FDP impactful and successful. So we sincerely hope this program has inspired new ideas, collaboration, and research direction with the domain of smart health innovation. Thank you once again. And I am requesting all the participants that I am sharing one assessment session. So you will have 1 hour to 2 hours to do your assessment by offline or from your home. That will be a assignment for you. So that form will be closed after 2 hours from the end of this FDP. So now I would like to request and invite Yuvnesh to deliver the vote of thanks.
Thank you, sir.
Yes, Dr. Yuvnesh.
Thanks for the words and invitation. So, good afternoon to one and all present here. It is indeed my proud privilege and honor to deliver the vote of thanks on behalf of organizing committee of this 6 days online faculty development program on smart health innovation, integrating imaging, sensors, and biometrics, jointly hosted by Department of Applied Mechanics, MIT Allahabad, and Department of Biotechnology and Bioengineering, School of Bioscience and Technology, Golgotia University. Over the past 6 days, we have embarked on intellectual stimulating journey enriched by insight lectures, thought-provoking discussion, and pioneer research shared by eminent scholars and domain experts from across the country. First and foremost, I express my deepest gratitude to our honorable chief partner, Professor R.S. Verma, Director MIT, for his inspiring vision and unwavering support, which has been instrumental in successful execution of these programs. We are equally thankful to Professor K. Mallikarjuna Babu, Honorable Vice Chancellor of Galgotia University, for his continued encouragement and guidance throughout. We extend our heartfelt gratitude and appreciation to our esteemed speaker and distinguished resource person, including Professor Gunalpal from MIT, Professor R.P. Tiwari from NIT Allahabad, Dr. Chandan Kumar, Shubha College of Engineering, Dr. Rishabh Singh, IIT Patna, Roshan Kumar Otta, IIT Jodhpur, Sharada Prasanna Malik, NIT AP, Vijay Kumar, Baba Saheb Bhima Rao, Ambedkar University Lucknow, Tayyab Khan, IIT Sonipat, Shreya Malhotra from IIT Kanpur, Sumit Tripathi, Goa Institute of Management, Sanjay Saxena, IIT Bhubaneswar, Munendra Singh, NIT Jamshedpur, Abhishek Kumar Tiwari, MNIT Allahabad, Uday Shankar, IIT BHU, Rajan Agrari, NIT Patna, Nishant Kumar, NIT Raipur, Sudeep Paul, NIT Raipur, Shivangi Giri, NIT Raipur, Dr. S. Parmanik, University of Allahabad, Dr. Indu Dore, MIT Allahabad, and many more. Your expert insight on topics ranging from medical robotics to bioprinting to artificial intelligence, biosensor, and advanced biometrics have added immense value to this FDP and have undoubtedly inspired both early career scholar and seasonal scholar. Special thanks are due to Dr. Ajay Bharati, Chairman, Dr. Gaurav Kumar, Organizing Secretary, without whom this FDP would have never been happened. Dr. Dheeraj Ahuja, Dr. Saurabh Bharadwaj, Dr. Somadipta Rakshit, Dr. Sumedha Mukherjee, Dr. Somnath Roy Chaudhary, and Dr. Anjali Priya for their unconditional coordination, detailed planning, and tireless effort that ensure the seamless conduction of each section. We also acknowledge with sincere gratitude the support of our session coordinators, technical staff, volunteers, backend team who behind the scheme effort were critical to smooth functioning of this program. A warm thank you to all our participants who joined from various academic and research institutes across the country, your active engagement, enthusiasm, and thoughtful question truly enriched our discussion. In conclusion, I extend my heartfelt gratitude, appreciation to everyone who contributed directly and indirectly to make this FDP a grand success. Let us carry forward the moment we have built here and continue to foster meaningful collaboration, innovation, and academic excellence. Thank you once again. Jai Hind.
Thank you so much, Yunesh, for your enlightening word. So now I am again thankful to all faculty member who have given the feedback. So one assessment link has been posted in the YouTube live link also in the chat box, and we have also posted in the chat box of Zoom. So I am requesting you all to kindly provide your feedback as well as do your assessment, and we will release the participation certificate to the eligible participant who has secured who have attended at least 4 FDP session and who will secure at least some marks in assessment. So as per the eligibility criteria, we will send their feedback, their certificate of participation on Monday. So okay, so thank you once again, you all. Okay. Can we close this meeting?
So they are asking to